The Big Bang happened 13.8 billion years ago. Every atom in your body, every star in the sky, every galaxy spinning through the void, all of it exploded into existence in that single moment. But new physics suggests something impossible occurred alongside our universe's birth. The equations demand it. The symmetry requires it. When the Big Bang erupted, it may have created not one universe, but 2 ours, expanding forward in time and another expanding backward. A perfect mirror where entropy decreases, where time flows in reverse, where the arrow of causality points the opposite direction. This is not philosophy. This is not speculation. This comes from peer-reviewed physics, published in Physical Review Letters, derived from CPT symmetry, one of the most fundamental principles in quantum field theory. The mirror universe exists in mathematics. Whether it exists in reality changes everything we understand about time, existence, and the nature of the cosmos itself. The CPT symmetry problem. Physics has rules that cannot be broken. Conservation laws govern every interaction, every particle collision, every force in nature. Energy is conserved. Momentum is conserved. Electric charge is conserved. But there exists another symmetry, more fundamental than these, woven into the fabric of quantum field theory itself. CPT symmetry combines 3 operations. Charge conjugation, which flips particles to antiparticles. Parity inversion, which mirrors spatial coordinates. And time reversal, which runs processes backward. The mathematics of quantum field theory demands that CPT symmetry must hold for every physical process. This is not a preference. This is a requirement of the equations themselves. The standard model of particle physics, which describes electromagnetic, weak, and strong nuclear forces, obeys CPT symmetry perfectly. Every experiment ever conducted confirms this. When physicists flip charge, parity, and time simultaneously in their equations, the laws of physics remain unchanged. The theory predicts this must be true universally. But our universe appears to violate this principle in the most profound way possible. We exist in a universe where time flows in one direction only forward. Entropy increases. Stars burn hydrogen and produce helium and heavier elements. Ice melts. Buildings crumble. Organisms age and die. The arrow of time points relentlessly toward the future. This creates a problem. If CPT symmetry is fundamental, if the laws of physics truly obey this principle, then the universe as a whole should also obey it. But our universe, taken by itself, does not. Time flows forward, not backward. Entropy increases, never decreases. The initial conditions at the Big Bang were extremely low entropy, all matter and energy compressed into an infinitesimally small point, and entropy has been rising ever since. This asymmetry appears to violate CPT symmetry unless something else exists to balance the equation. In 2018, physicists Latham Boyle, Kieran Finn, and Neil Turok from the Perimeter Institute for Theoretical Physics published a paper in Physical Review Letters proposing a radical solution. They argued that CPT symmetry could be preserved if the Big Bang created not one universe, but 2 ours, and a mirror universe on the opposite side of the singularity. In their model, the mirror universe expands backward in time relative to ours. From our perspective, time flows forward. From the mirror universe's perspective, their time also flows forward. But relative to each other, the 2 universes are time reversed. Our universe has increasing entropy moving forward. The mirror universe has increasing entropy moving backward. The symmetry is restored. The mathematics behind this proposal emerges from general relativity and quantum field theory. Einstein's equations allow for solutions where spacetime extends on both sides of a singularity. Normally, physicists discard the other side as unphysical, a mathematical artifact with no real meaning. But Boyle, Finn, and Turok showed that if you take CPT symmetry seriously, that other side must exist. It is not optional. The mirror universe is required by the fundamental symmetries of physics. Without it, the universe violates the principles that govern every particle interaction. The implications are staggering. In this mirror universe, time runs backward from our perspective. If an observer could somehow view both universes simultaneously, they would see our Big Bang explosion expanding into the future, while the mirror Big Bang expands into the past. Both universes experience time moving forward within their own frames, but the direction of forward is opposite. Entropy increases in both directions away from the shared singularity. The total system, both universes combined, has perfect time symmetry. This solves another deep puzzle in cosmology, the initial conditions problem. Why did the universe start in such an extraordinarily low entropy state? In a single universe, this seems like an absurd coincidence. The probability of all matter and energy beginning in such an organized configuration is incomprehensibly small. But if two universes emerge from the singularity, expanding in opposite temporal directions, the low entropy starting point is natural. It is simply the midpoint, the moment of maximum symmetry from which both universes diverge. The CPT symmetric universe model also addresses the cosmological arrow of time. Physicists have long wondered why time has a direction at all. The fundamental laws of physics, Newton's laws, Maxwell's equations, quantum mechanics, even general relativity, are time reversible. Run any of these equations backward, and they still describe valid physical processes. Yet our universe clearly distinguishes the past from the future. The second law of thermodynamics states that entropy always increases, defining time's arrow. But why? In the mirror universe model, the answer is simple. The universe started at a point of minimum entropy, and both time directions lead away from that point toward higher entropy. The arrow of time is not imposed from outside. It emerges naturally from the symmetry of the system. Experimental evidence for CPT symmetry comes from particle physics. Every measurement ever made confirms that antimatter behaves as predicted when you flip charge, parity, and time. The properties of antiparticles, positrons, antiprotons, antineutrons match precisely what CPT symmetry predicts. No violation has ever been detected at the particle level. The question is whether this microscopic symmetry must also hold at the cosmological scale. Boyle, Finn, and Turok argue it must. If CPT symmetry governs particle interactions, it must govern the universe as a whole. Critics point out that the mirror universe remains undetectable. We cannot observe it directly because it exists on the other side of the Big Bang singularity, a region of spacetime we cannot access. Light cannot travel through a singularity. No information can cross that boundary. From within our universe, the mirror universe is invisible, forever hidden behind the moment of creation. But theoretical physics often deals with entities that cannot be directly observed: dark matter, the interiors of black holes, the quantum wave function. What matters is whether the theory makes testable predictions and whether it solves existing problems. The mirror universe does both. The dark matter connection. Dark matter is one of cosmology's greatest mysteries. Observations from galaxy rotation curves, gravitational lensing, and the cosmic microwave background radiation conclusively demonstrate that 85% of the universe's matter does not emit, absorb, or reflect electromagnetic radiation. It is invisible to telescopes, but reveals itself through gravity. Galaxies spin too fast. Galaxy clusters contain more mass than their visible matter suggests. The structure of the cosmic web requires far more gravitational pull than ordinary matter provides. Dark matter exists, but what is it? For decades, physicists proposed various candidates. WIMPs, weakly interacting massive particles, dominated early searches. Experiments buried deep underground, shielded from cosmic rays, searched for dark matter particles colliding with ordinary atoms. None were found. Axions, another candidate, remain undetected despite sophisticated searches. Primordial black holes, sterile neutrinos, modified gravity theories, each possibility has problems. Dark matter's identity remains unknown. The mirror universe model offers an unexpected answer. In 2019, Boyle, Finn, and Turok extended their CPT symmetric cosmology to explain dark matter without invoking new particles. Their key insight: the mirror universe and our universe are not completely isolated. Though separated by the Big Bang singularity, they are connected through gravity. Gravity is unique among fundamental forces because it does not require charge or other quantum numbers to act. Gravitational fields can extend across space-time boundaries in ways that electromagnetic or nuclear forces cannot. In this picture, dark matter is ordinary matter, but it exists in the mirror universe. The mass of stars, planets, gas, and dust in the mirror universe exerts gravitational influence on our universe. We feel the gravity of their matter, but we cannot see their light because photons cannot cross the singularity. Their electromagnetic radiation remains trapped in their universe. Only their gravitational field penetrates into ours. To us, this appears as dark matter mass that gravitates but does not shine. The mathematics works precisely. The mirror universe contains the same types of particles as ours: protons, neutrons, electrons, just arranged in a CPT inverted configuration. Their matter distribution mirrors ours. Where we have galaxy clusters, they have galaxy clusters. Where we have voids, they have voids. The gravitational fields overlap, creating the dark matter halos we observe surrounding galaxies and pervading the cosmic web. The amount of dark matter we detect matches exactly what you would expect if a mirror universe exists on the other side of the Big Bang. This explains dark matter's distribution. Dark matter is not distributed randomly. It forms halos around galaxies, filaments connecting galaxy clusters, and cosmic web structures that mirror the distribution of ordinary matter. Traditional dark matter models struggle to explain why dark matter's distribution so closely follows ordinary matter's distribution. If dark matter consists of exotic particles interacting only through gravity and the weak force, why does it trace the same large-scale structure as ordinary matter? The mirror universe model provides a natural explanation. Dark matter follows ordinary matter's distribution because it is ordinary matter just in the mirror universe, where the structures formed through the same gravitational processes that shaped our universe. Galaxy rotation curves provide strong evidence. When astronomers measure how fast stars orbit within galaxies, they find that orbital speeds remain constant even far from the galactic center. Newtonian gravity predicts speeds should decrease with distance, just as planets farther from the Sun orbit more slowly. The flat rotation curves require additional mass dark matter halos extending far beyond the visible stars. In the mirror universe model, this extra mass comes from the mirror galaxy's gravitational field. Our Milky Way and its mirror counterpart both contribute to the total gravitational potential, producing the observed rotation curves without requiring exotic particles. Gravitational lensing observations confirm this. When light from distant galaxies passes near massive galaxy clusters, it bends around them, creating distorted arcs and multiple images. The amount of bending depends on the total mass present. Measurements consistently show that galaxy clusters contain 5 times more mass than their visible matter. This missing mass is dark matter. In the mirror universe scenario, half of this mass comes from ordinary matter in our universe, and half comes from the mirror universe's matter gravitationally coupled to ours. The 5-to-1 ratio emerges naturally from the symmetry. The cosmic microwave background radiation provides additional support. The CMB, the afterglow of the Big Bang, contains tiny temperature fluctuations that seeded galaxy formation. These fluctuations' pattern depends on the universe's matter content. Precise measurements from the Planck satellite show that ordinary matter comprises roughly 5% of the universe's total energy density. Dark matter comprises 27%, and dark energy comprises 68%. If dark matter is mirror universe matter, this ratio makes sense. Our universe and the mirror universe together contain equal amounts of ordinary matter, but we observe their combined gravitational effects, making dark matter appear roughly 5 times more abundant than the ordinary matter we can see. Direct detection experiments searching for dark matter particles consistently find nothing. Dozens of experiments worldwide have searched for WIMPs, axions, and other candidates for decades. The null results are puzzling if dark matter consists of new particles in our universe. But if dark matter is ordinary matter in the mirror universe, direct detection is impossible. Mirror universe particles cannot enter our detectors. Their electromagnetic interactions occur entirely within their universe. Only their gravity reaches across the singularity. The failure to detect dark matter particles becomes evidence for, rather than against, the mirror universe hypothesis. One testable prediction emerges. Dark matter should behave exactly like ordinary matter gravitationally. It should clump into structures, form halos, and interact through gravity alone, precisely what observations show. Alternative dark matter candidates often predict different behaviors. Self-interacting dark matter models suggest dark matter particles should collide with each other, smoothing out small-scale structures. But observations show dark matter behaves collisionlessly, passing through itself without interaction exactly as mirror universe matter would, since mirror particles cannot interact with each other across the singularity except through gravity. Neutrinos and the asymmetry. The universe contains a profound asymmetry. Matter dominates over antimatter. Every star, planet, and galaxy consists of protons, neutrons, and electrons, not their antimatter counterparts. When the Big Bang occurred, physics predicted equal amounts of matter and antimatter should have formed. As the universe cooled, matter and antimatter should have annihilated, leaving only photons. Yet we exist. Somehow, a tiny excess of matter survived roughly 1 extra matter particle for every billion matter-antimatter pairs. This excess became everything we see. The source of this asymmetry remains one of physics' deepest mysteries. The standard model of particle physics cannot explain matter-antimatter asymmetry. The model includes CP violation processes where charge parity symmetry breaks, but the amount of CP violation observed is far too small to account for the universe's matter content. Something beyond the standard model must explain why we exist in a matter-dominated universe. Many physicists believe neutrinos hold the key. Neutrinos are ghostly particles that barely interact with ordinary matter. Trillions pass through your body every second from the sun. yet you never notice. They have tiny masses, much smaller than electrons, and come in three types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. They oscillate between these flavors as they travel through space, a quantum effect that proves they have mass. But the origin of neutrino mass remains unclear. The Standard Model originally predicted neutrinos were massless. The discovery that they have mass requires extending the theory. One possibility is that neutrinos are Majorana particles, meaning they are their own antiparticles. For most particles, matter and antimatter are distinct. An electron and a positron are different. A proton and an antiproton are different. But Majorana particles are identical to their antiparticles. If neutrinos are Majorana particles, this opens a pathway to explain matter-antimatter asymmetry through a process called leptogenesis. In the early universe, heavy Majorana neutrinos could have decayed asymmetrically, producing more matter leptons than antimatter leptons. This imbalance could have converted into the baryon asymmetry we observe today. The mirror universe model makes a specific prediction about neutrinos. In our universe, we observe three types of light neutrinos, but the model predicts there should also be right-handed neutrinos, sterile neutrinos, that do not interact through the weak force. These sterile neutrinos would be extremely difficult to detect because they interact only through gravity and possibly through mixing with ordinary neutrinos. In the CPT symmetric cosmology, right-handed neutrinos are not separate particles. They are left-handed neutrinos from the mirror universe. This solves multiple problems simultaneously. First, it explains why right-handed neutrinos have not been observed. They exist in the mirror universe, not ours. Second, it provides a natural mechanism for neutrino masses. Neutrinos acquire mass through mixing between left-handed neutrinos in our universe and right-handed neutrinos in the mirror universe. This mixing occurs through gravity, which can couple particles across the singularity. Third, it explains leptogenesis and matter-antimatter asymmetry. The decay of heavy neutrinos in the early universe produces more matter in our universe and more antimatter in the mirror universe. Each universe has opposite asymmetry, but the total system is symmetric. Experimental searches for sterile neutrinos have yielded ambiguous results. Some experiments, like the liquid scintillator neutrino detector, LSND, and Mini-Boo-Ni, reported anomalies consistent with sterile neutrinos. Others found no evidence. The mirror universe model suggests these ambiguities arise because sterile neutrinos do not exist as independent particles in our universe. The signals interpreted as sterile neutrinos might instead be subtle effects from mirror universe neutrinos gravitationally mixing with ordinary neutrinos. Neutrino oscillations provide a testing ground. Neutrinos change flavor as they propagate electron. Neutrinos turn into muon neutrinos, which turn into tau neutrinos, oscillating continuously. The oscillation parameters depend on neutrino masses and mixing angles. Precision measurements from experiments like T2K, NOVA, and Super Kamiokande have determined most of these parameters. However, several anomalies remain unexplained. The mirror universe model predicts additional oscillation channels involving mirror neutrinos. These would manifest as tiny deviations from the standard three-flavor oscillation predictions. The seesaw mechanism, a popular explanation for small neutrino masses, fits naturally into the mirror universe framework. The seesaw mechanism proposes that neutrinos have small masses because they mix with very heavy right-handed neutrinos. The large mass of the right-handed neutrinos suppresses the mass of the ordinary left-handed neutrinos through quantum mixing. In the mirror universe model, these heavy right-handed neutrinos are mirror universe particles coupled to our neutrinos through gravitational interactions across the singularity. The mechanism works identically, but the interpretation changes. The heavy neutrinos are not new particles, but mirror universe counterparts. Matter-antimatter asymmetry measurements come from multiple sources. The cosmic microwave background temperature fluctuations encode the baryon to photon ratio, the number of matter particles relative to photons. Measurements give a value of about 6 times 10, -10, meaning roughly 1 matter particle exists for every 1.6 billion photons. Big Bang nucleosynthesis, the formation of light elements in the early universe, provides an independent measurement, yielding consistent results. Both measurements confirm a tiny but crucial matter excess. The mirror universe model explains this asymmetry naturally. Our universe has excess matter, the mirror universe has excess antimatter. The total system is symmetric. Upcoming experiments will test these predictions. The Deep Underground Neutrino Experiment, DUNE, currently under construction, will measure neutrino oscillations with unprecedented precision. If the mirror universe model is correct, DUNE should detect anomalies in the oscillation parameters, small deviations from the three-flavor model caused by mixing with mirror neutrinos. The Hyper Kamiokande detector in Japan, scheduled to begin operations in the late 2020s, will search for proton decay and rare neutrino interactions. Any unexpected signals could point toward mirror universe physics. Inflation and the mirror bounce. Cosmic inflation is the cornerstone of modern cosmology. In the first fraction of a second after the Big Bang, the universe underwent exponential expansion, growing from subatomic scales to astronomical scales in 10⁻32 seconds. This inflationary period explains why the universe appears flat, homogeneous, and isotropic on large scales. It explains why distant regions of the universe, which have never been in causal contact, have the same temperature. It explains the origin of cosmic structure. Quantum fluctuations during inflation were stretched to cosmic scales, seeding the galaxies and clusters we observe today. But inflation creates a problem for the mirror universe model. Standard inflation theory assumes the universe began in a hot, dense state and expanded exponentially. This expansion diluted any pre-existing structure and smoothed out irregularities. After inflation ended, the universe reheated, creating the hot plasma of the early universe. This picture works beautifully for a single universe, but if two universes exist on opposite sides of the Big Bang singularity, expanding in opposite temporal directions, how does inflation fit? Boyle, Finn, and Turok addressed this in their 2020 paper, extending the CPT symmetric cosmology to include inflation. Their solution is elegant. Instead of inflation occurring after the Big Bang, it occurs before in a pre-Big Bang phase. The universe bounces at the singularity, transitioning from a contracting phase into an expanding phase. Inflation happens symmetrically on both sides of the bounce. Our universe inflates forward in time. The mirror universe inflates backward in time. Both universes emerge from the same inflationary epoch, expanding away from the singularity in opposite temporal directions. This mirror bounce scenario differs fundamentally from standard inflation. In standard inflation, the inflaton field, a hypothetical scalar field driving inflation, starts in a high energy state and slowly rolls down its potential energy curve. As it rolls, it releases energy, driving exponential expansion. When the field reaches the minimum of its potential, inflation ends and the field's energy converts into particles, reheating the universe. In the mirror bounce model, the inflaton field behaves symmetrically around the singularity. It reaches its maximum energy at the bounce point and rolls down symmetrically in both temporal directions. Both universes experience identical inflation but in opposite time directions. The quantum fluctuations generated during inflation create the seeds for cosmic structure. These fluctuations are nearly scale invariant. They have similar amplitude at all scales, a prediction confirmed by measurements of the cosmic microwave background. In the mirror bounce model, these fluctuations are CPT symmetric. The fluctuations in our universe mirror those in the other universe. If our universe has a density enhancement at a certain location, the mirror universe has a corresponding enhancement at the mirror location. The pattern is symmetric. This resolves a long-standing puzzle. Why does inflation produce scale-invariant fluctuations? In standard inflation, the scale invariance emerges from the inflaton field's dynamics, but it is sensitive to the field's potential energy shape. Different potential shapes produce different fluctuation spectra. The mirror bounce model predicts scale invariance automatically from CPT symmetry. The fluctuations must be scale invariant because the laws of physics are symmetric under time reversal. The observation that the universe's fluctuations are nearly scale invariant becomes evidence for CPT symmetry at cosmological scales. The model makes testable predictions about primordial gravitational waves. Inflation generates not only density fluctuations, but also gravitational wave fluctuations, ripples in space-time itself, produced by quantum effects during the exponential expansion. These gravitational waves leave an imprint in the cosmic microwave background as B-mode polarization, a curl pattern in the CMB's polarization that standard density fluctuations cannot produce. Detecting primordial B-modes would confirm inflation occurred and provide information about the energy scale of inflation. In the mirror bounce model, gravitational waves are symmetric across the singularity. Our universe and the mirror universe both produce identical gravitational wave spectra. However, because the universes expand in opposite time directions, the gravitational waves propagate differently. In our universe, they travel forward in time. In the mirror universe, they travel backward. From our perspective, this symmetry means the gravitational wave spectrum should have specific properties, particular correlations between different scales, that distinguish mirror bounce inflation from standard inflation. Current observations constrain but do not yet detect primordial gravitational waves. The Planck satellite and Bicep-Keck array experiments have measured the CMB polarization with increasing precision. No B-mode signal from inflation has been conclusively detected, but upper limits continue to tighten. If the mirror bounce model is correct, future experiments like CMB-S4 and Light-Beard should eventually detect the B-mode signal, and its properties should match the mirror bounce predictions rather than standard inflation. The bounce itself requires new physics. General relativity predicts singularities points where space-time curvature becomes infinite and the equations break down. At the Big Bang singularity, classical general relativity fails. Quantum gravity effects become important. We do not yet have a complete theory of quantum gravity, but physicists expect that quantum effects prevent true singularities from forming. Instead of infinite density and curvature, quantum gravity likely produces a bounce, a smooth transition from contraction to expansion. Loop quantum cosmology, one approach to quantum gravity, predicts exactly this behavior. In loop quantum cosmology, space-time becomes granular at the Planck scale, the smallest possible length scale, about 10⁻35 meters. At this scale, quantum geometry effects prevent the universe from collapsing to a singularity. Instead, the universe bounces. The density reaches a maximum value, and the collapsing universe transitions into an expanding universe. The mirror universe model fits naturally into this framework. The bounce-in-loop quantum cosmology is the same bounce that separates our universe from the mirror universe. String theory offers another avenue. In string theory, fundamental particles are not point-like, but one-dimensional strings. The theory requires extra spatial dimensions beyond the three we observe. At high energies, near the Planck scale, these extra dimensions and stringy effects become important. Some string cosmology models predict bounces or cyclic universes where contraction and expansion alternate. The mirror universe could emerge from string theory as a natural consequence of the theory's symmetries. The mirror bounce also addresses the horizon problem differently than standard inflation. The horizon problem asks why distant regions of the universe have the same temperature even though they have never been in causal contact. Standard inflation solves this by proposing that these regions were in contact before inflation, and inflation stretched them apart. The mirror bounce model solves it differently. The regions were in causal contact before the bounce, in the contracting phase. Information could propagate between them during contraction. When the bounce occurred, this information was preserved symmetrically in both universes. Observable consequences. A theory must make predictions. Without testable predictions, it is philosophy, not physics. The mirror universe model, despite describing regions of space-time we cannot directly observe, makes specific predictions about phenomena in our observable universe. These predictions distinguish it from standard cosmology and provide pathways to confirm or falsify the model through observations and experiments. The cosmic microwave background radiation is the most powerful probe. The CMB is the afterglow of the Big Bang, light that has travelled through the universe for 13.8 billion years since the moment when neutral atoms first formed. Tiny temperature fluctuations in the CMB variations of 1 part in 100,000 encode information about the early universe's structure, composition, and dynamics. The Planck satellite measured these fluctuations with extraordinary precision, creating a detailed map of the infant universe. The mirror universe model predicts specific features in the CMB power spectrum, the graph showing fluctuation amplitude versus angular scale. Standard inflation predicts a nearly scale-invariant power spectrum with small deviations. The mirror bounce inflation predicts similar scale invariance, but with subtle differences. The spectral index, the slope of the power spectrum, should have a specific value determined by CPT symmetry. Measurements from Planck show a spectral index of 0.965, very close to, but slightly different from 1, which represents perfect scale invariance. The mirror universe model predicts this deviation's exact value based on the symmetry requirements. Gravitational waves from inflation provide another test. As discussed earlier, inflation generates primordial gravitational waves that imprint B-mode polarization patterns in the CMB. The mirror bounce model predicts the amplitude and spectral shape of these gravitational waves. The tensor to scalar ratio, the ratio of gravitational wave fluctuations to density fluctuations, should have a specific value. Current observations place upper limits on this ratio, but have not yet detected it. Future experiments, particularly LightBeard, scheduled for launch in the late 2022, and CMBS-4 ground-based telescopes, will reach the sensitivity required to detect or rule out the mirror bounce predictions. Neutrino experiments offer direct tests. The model predicts right-handed neutrinos exist in the mirror universe and couple to our neutrinos through gravity-mediated mixing. This produces small anomalies in neutrino oscillation experiments, deviations from the standard three-flavor neutrino model. Experiments like DUNE, under construction in South Dakota, will measure neutrino oscillations with precision sufficient to detect these anomalies if they exist. DUNE will send neutrino beams from Fermilab in Illinois to detectors 800 miles away in South Dakota, measuring how neutrinos oscillate during their journey. Any unexpected oscillation patterns could indicate mirror universe neutrino mixing. Dark matter detection experiments provide indirect tests. If dark matter consists of mirror universe ordinary matter rather than exotic particles, direct detection experiments should continue to find nothing. Experiments like LUX-ZEPPELIN and XEONNT, buried deep underground to shield from cosmic rays, search for dark matter particles colliding with xenon atoms. Decades of searching have yielded null results. The mirror universe model explains why. Mirror universe particles cannot enter our detectors. They interact only through gravity, making direct detection impossible. The continued absence of detection supports the model, though it does not prove it, since other explanations for dark matter's invisibility exist. Gravitational wave astronomy opens new windows. The LIGO and Virgo detectors have detected dozens of black hole mergers since 2015, measuring gravitational waves from colliding black holes and neutron stars. Future space-based detectors like LISA, scheduled for launch in the 2032, will detect gravitational waves from supermassive black hole mergers and other sources invisible to ground-based detectors. The mirror universe model predicts these gravitational waves should have specific properties related to the CPT symmetry. Subtle correlations between gravitational wave signals at different frequencies could reveal signatures of the mirror universe's influence. Baryon asymmetry measurements constrain the model. The mirror universe explains why our universe has excess matter. The mirror universe has excess antimatter, balancing the asymmetry. The observed baryon to photon ratio, measured from the CMB and Big Bang nucleosynthesis, should match the model's predictions based on leptogenesis from neutra decay. Current measurements give a ratio of about 6 times 10, -10. The mirror universe model must reproduce this exact value from the dynamics of neutrino decay in the early universe. Recent calculations by Boyle and collaborators show that the model can match the observed ratio, but the match depends on specific parameters, the masses of heavy neutrinos, and the strength of their coupling. Precision measurements of these parameters provide a test of the model's validity. Cosmic structure formation offers another observational test. The distribution of galaxies, galaxy clusters, and voids follows patterns determined by gravitational collapse of primordial density fluctuations. The mirror universe contributes gravitationally to structure formation. Dark matter halos surrounding galaxies should have specific shapes and density profiles determined by the combined gravity of both universes. Observations from galaxy surveys, like the Sloan Digital Sky Survey, and upcoming missions like Euclid Map Structure across cosmic time. Comparing these observations with simulations including mirror universe gravity tests whether the predicted structure matches reality. The Hubble tension, the disagreement between different measurements of the universe's expansion rate, might connect to mirror universe physics. Local measurements using supernova distances give a Hubble constant of about 73 km per second per megaparsec. Measurements from the CMB give about 67 km per second per megaparsec. This 9% discrepancy persists despite improved measurements. Some physicists speculate that new physics in the early universe might resolve the tension. The mirror universe model modifies early universe dynamics through the symmetric bounce and could potentially affect the expansion history in ways that reconcile the measurements. Primordial black holes provide a possible smoking gun. If the mirror universe exists, quantum fluctuations near the bounce could create microscopic black holes that survive to the present. These primordial black holes would have specific mass distributions determined by the bounce dynamics. Searches for primordial black holes through gravitational lensing, gravitational waves, and their effects on cosmic structure constrain their abundance. The mirror universe model predicts specific populations of primordial black holes. Finding black holes with the predicted mass distribution would strongly support the model. Conversely, ruling out these populations would challenge it. The cosmological constant problem why dark energy has the tiny but non-zero value observed might relate to mirror universe physics. Dark energy's energy density is 10, 100, and 20 times smaller than naive quantum field theory predictions. This discrepancy is physics' most severe fine-tuning problem. Some versions of the mirror universe model suggest that dark energy's value emerges from quantum effects in the symmetric bounce. If the vacuum energy must be symmetric across the bounce, this constraint might naturally produce a small but non-zero cosmological constant. Testing this requires understanding quantum field theory in curved spacetime near singularities, which remains an open problem in quantum gravity. High-energy cosmic rays, particles from space, with energies far exceeding anything produced in particle accelerators, might carry mirror universe signatures. If mirror universe particles can convert to ordinary particles through rare quantum processes, ultra-high energy cosmic rays could contain a component originating from the mirror universe. The Pierre Auger Observatory in Argentina detects the highest energy cosmic rays and measures their arrival, directions, and energies. Anomalies in the cosmic ray spectrum, or unexpected arrival patterns, might indicate mirror universe contributions, though disentangling such signals from astrophysical sources is challenging. Precision measurements of fundamental constants provide subtle tests. If the mirror universe affects our universe through gravity, this could slightly modify the effective values of constants like Newton's gravitational constant or the fine structure constant over cosmic time. Comparing measurements of these constants at different cosmic epochs using distant quasars as cosmic laboratories constrains how much they can vary. The mirror universe model predicts these constants should remain fixed within tight bounds. Any detected variation would challenge the model, while continued consistency supports it. Alternative theories and competitors. The mirror universe model is not the only proposal to address cosmology's deep problems. Multiple competing theories attempt to explain dark matter, matter-antimatter asymmetry, and the arrow of time through different mechanisms. Comparing these alternatives helps clarify the mirror universe model's strengths and weaknesses. Supersymmetry proposes that every known particle has a superpartner with different spin. The lightest supersymmetric particle, possibly the neutralino, could be dark matter. Supersymmetry would explain why the Higgs boson's mass is stable against quantum corrections and could unify the fundamental forces at high energies. The Large Hadron Collider has searched extensively for supersymmetric particles. None have been found. Each null result pushes supersymmetry toward higher masses and more contrived parameter regions. While not ruled out, supersymmetry's parameter space is increasingly constrained. Axions offer another dark matter candidate. Proposed originally to solve the strong CP problem in quantum chromodynamics, axions are ultralight particles that could fill the universe with dark matter. Multiple experiments search for axions through their conversion to photons in strong magnetic fields. The Axion Dark Matter Experiment, ADMX, and other detectors have ruled out some axion mass ranges, but much parameter space remains. If discovered, axions would explain dark matter without requiring a mirror universe. But axions don't address the other problems the mirror universe solves: neutrino masses, matter-antimatter asymmetry, and the arrow of time. Modified gravity theories, like MOND, modified Newtonian dynamics, propose that gravitational law changes at low accelerations rather than invoking dark matter. MOND successfully explains galaxy rotation curves without dark matter, but it fails to explain gravitational lensing by galaxy clusters, the cosmic microwave background, and large-scale structure formation. Most physicists consider MOND ruled out by these observations, though variants like TVIS, tensor vector scalar gravity, attempt to address these problems while retaining MOND's successes. Primordial black holes, formed in the early universe from density fluctuations, could constitute dark matter. These black holes would range from asteroid masses to thousands of solar masses. Searches through gravitational microlensing and gravitational waves constrain their abundance in many mass ranges. Recent detections of black hole mergers by LIGO have renewed interest in primordial black holes as dark matter candidates. However, current constraints make it unlikely that primordial black holes account for all dark matter, though they could contribute partially. Asymmetric dark matter theories propose that dark matter has a matter-antimatter asymmetry parallel to ordinary matter's asymmetry. In these models, dark matter and ordinary matter asymmetries are generated simultaneously in the early universe through related processes. This explains why dark matter density is roughly 5 times ordinary matter density. Both arise from the same asymmetry generating mechanism. These theories predict dark matter should have similar abundance to ordinary matter, which matches observations. However, they require new particles and forces beyond the standard model, without explaining why those particles exist. Cyclic cosmology models propose the universe undergoes infinite cycles of expansion and contraction. Each cycle ends in a big crunch, followed by a bounce into a new expansion phase. These models avoid the initial conditions problem by extending time infinitely into the past. However, they face severe obstacles. Entropy increases with each cycle, making the cycles progressively longer. Extrapolating backward, earlier cycles become shorter, and the model still requires a beginning. Additionally, quantum effects near the bounce are poorly understood, and general relativity predicts singularities that might prevent bounces. String theory's landscape, with 10,500 possible vacuum states, suggests our universe might be one among countless others with different physical laws. Dark matter, matter-antimatter asymmetry, and other properties could result from anthropic selection. We observe values that permit life, because only such values allow observers to exist. This explains apparent fine-tuning, but makes no predictions about specific values. Without a mechanism to scan the landscape or understand the probability distribution over vacua, the landscape provides explanation only in hindsight. Each alternative addresses some problems, but leaves others unsolved. Supersymmetry might explain dark matter, but doesn't naturally explain matter-antimatter asymmetry, or the arrow of time. Axions solve dark matter and the strong CP problem, but require additional mechanisms for asymmetry. Modified gravity eliminates dark matter, but fails observational tests. Primordial black holes provide dark matter, but don't address asymmetry or time's arrow. Asymmetric dark matter explains the matter-dark matter density ratio, but requires new particles without deeper explanation. The mirror universe model's strength is comprehensiveness. It addresses dark matter, neutrino masses, matter-antimatter asymmetry, the arrow of time, and the initial conditions problem through a single principle, CPT symmetry. This parsimony is attractive. Rather than adding new particles, forces, or arbitrary initial conditions, the model extends known physics symmetrically. CPT symmetry is not speculative, It's confirmed in every particle physics experiment. The mirror universe hypothesis merely takes this symmetry seriously at cosmological scales. However, the model has weaknesses. It is difficult to test directly. The mirror universe is unobservable except through gravity. Many predictions are subtle small deviations in neutrino oscillations, specific patterns in gravitational waves, particular CMB features. These require experiments at the edge of current technology. Furthermore, the model requires quantum gravity near the bounce, and we lack a complete quantum gravity theory. Until loop quantum cosmology, string theory, or another approach provides a solid foundation for the bounce, the model's details remain uncertain. Another criticism is that the mirror universe seems contrived. Why should the universe be CPT symmetric globally when we don't observe other global symmetries? Spatial homogeneity and isotropy emerge from inflation's dynamics, not from imposed symmetry. Why should time's direction be different? Proponents respond that CPT symmetry is more fundamental than spatial symmetries. It emerges from the structure of quantum field theory itself, not from dynamics. If quantum field theory is correct, and experiments consistently confirm it, CPT symmetry must hold. The mirror universe is not an add-on, but a necessary consequence of taking known physics seriously. The road to confirmation. Science advances through prediction and observation. The mirror universe model makes predictions. Can observations confirm or refute them? Several experimental and observational programs underway or planned could provide evidence within the next 2 decades. The Deep Underground Neutrino experiment represents the most direct test. DUNE will send neutrino beams 800 miles through Earth, from Fermilab in Illinois to detectors in South Dakota. By measuring how neutrinos oscillate during this journey, DUNE will determine neutrino masses and mixing parameters with unprecedented precision. The mirror universe model predicts specific deviations from 3-flavor oscillations caused by mixing with mirror universe neutrinos. These deviations are small, typically a few percent, but DUNE's sensitivity should detect them if they exist. Results are expected in the late 2020 seconds. The Hyper-Kamiokande detector in Japan will complement DUNE. This massive water Cherenkov detector, 260 meters underground, and containing 260,000 tons of ultra-pure water, will study neutrinos from the sun, atmosphere, and artificial beams. It will search for proton decay, test neutrino properties, and observe supernova neutrinos. Any unexpected features in neutrino behavior could indicate mirror universe physics. Hyper-Kamiokande is scheduled to begin operations in 2027. CMB observations will continue improving. The Simons Observatory and CMB-S4 project will map the cosmic microwave background's polarization with sensitivity sufficient to detect or rule out primordial gravitational waves from inflation. The mirror bounce model predicts specific gravitational wave amplitudes and spectral features. If detected gravitational waves match the predictions, this would strongly support the model. If the observed spectrum differs, or if no gravitational waves are detected despite sufficient sensitivity, this would challenge the model. Results are expected in the early 2030 seconds. The LightBird satellite, a Japanese-led mission scheduled for launch in 2028, will measure CMB polarization from space, avoiding atmospheric contamination. With sensitivity to tensor-to-scalar ratios as small as 0.001, about 10 times better than current limits, LightBird will probe the energy scale of inflation. The mirror bounce model's predictions fall within LightBird's sensitivity range. Detection or non-detection will constrain the model's viability. Gravitational wave observations from LISA will test mirror universe predictions. LISA, a space-based gravitational wave detector consisting of 3 spacecraft in a triangular formation will detect low-frequency gravitational waves invisible to ground-based detectors like LIGO. It will observe supermassive black hole mergers, extreme mass ratio in spirals, and potentially primordial gravitational waves. The mirror universe model predicts specific correlations in the gravitational wave background. LISA's launch is planned for the mid-2030s. Dark matter searches will continue. While the mirror universe model predicts direct detection experiments will find nothing, this prediction is not unique. Many dark matter candidates are undetectable directly. However, astrophysical observations can test the model's specific predictions about dark matter's distribution and behavior. The Vera Rubin Observatory, beginning operations in 2024, will survey the entire southern sky every few nights, mapping dark matter through gravitational lensing. Its measurements of dark matter halo shapes and distributions can test whether dark matter behaves as the mirror universe model predicts. Neutrinoless double beta decay experiments test whether neutrinos are Majorana particles. In this hypothetical process, a nucleus converts 2 neutrons into 2 protons, emitting 2 electrons but no neutrinos. Only possible if neutrinos are their own antiparticles. Experiments like Legend, Nexo, and Cupid search for this decay. If neutrinos are Majorana particles, as the mirror universe model suggests, these experiments might detect the process. Conversely, failure to detect it after reaching sufficient sensitivity would challenge the model. Precision cosmology measurements will test the model's structure formation predictions. The Euclid satellite, launched in 2023, will map galaxy distributions across 10 billion years of cosmic history. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2022, will complement Euclid with high-resolution imaging and spectroscopy. Both missions will measure dark energy's properties and test gravity on cosmic scales. Any deviations from standard cosmology predictions could indicate mirror universe effects. Laboratory tests of CPT symmetry continue improving. Anti-hydrogen experiments at CERN, including alpha and base, measure antimatter properties with extraordinary precision. They compare hydrogen and antihydrogen atoms, searching for any difference in their spectra, gravitational behavior, or other properties. Finding any CPT violation would revolutionize physics. The mirror universe model relies on perfect CPT symmetry, so any violation would refute it. Conversely, continued confirmation of CPT symmetry at higher precision supports the model's foundation. Quantum information experiments might probe time symmetry. Some quantum foundations researchers are developing experiments to test time-symmetric quantum mechanics using weak measurements and post-selection. If these experiments confirm that quantum systems carry information about both past and future boundary conditions, this would support the mirror universe model's interpretation of quantum mechanics. However, interpretations of quantum mechanics are notoriously difficult to test definitively. The convergence of multiple independent tests provides the best path to confirmation. No single experiment will definitively prove the mirror universe exists. But if neutrino anomalies appear in Dune, gravitational waves match mirror bounce predictions in Lightbird, dark matter distributions fit mirror universe simulations in Vera Rubin Observatory data, and neutrinoless double beta decay is detected all consistent with the same theoretical framework, confidence in the model would grow significantly. Conversely, any clear contradiction would refute the model. If Dune detects no oscillation anomalies despite sufficient sensitivity, or if primordial gravitational waves are detected with properties incompatible with mirror bounce inflation, or if neutrinos are proven not to be Majorana particles, the model would need revision or abandonment. This falsifiability is crucial. The mirror universe model makes specific, testable predictions that distinguish it from alternatives. Baryon acoustic oscillations. The universe contains a fossil, a pattern, imprinted in the distribution of galaxies that reveals conditions 380,000 years after the Big Bang. This pattern, called baryon acoustic oscillations, appears as a characteristic scale in how galaxies cluster together across cosmic distances. Measuring this scale provides one of cosmology's most precise rulers, allowing astronomers to determine how the universe has expanded over billions of years. The measurement reveals details about dark energy, cosmic geometry, and the universe's composition that connect directly to questions about the mirror universe's existence. Before the cosmic microwave background formed, the universe was a hot plasma where photons, electrons, protons, and neutrons interacted constantly. Photons scattered off free electrons, preventing light from traveling freely. This plasma contained density fluctuations, regions slightly denser than average seeded by quantum fluctuations during inflation. These fluctuations created pressure waves, sound waves propagating through the plasma at about 57% of light speed. Each density fluctuation generates an expanding spherical wave, like dropping a stone in a pond creates expanding ripples. But these were three-dimensional spherical ripples, expanding outward from each initial fluctuation point. The waves consisted of alternating compressions and rarefactions, regions of higher and lower density propagating through the primordial plasma. The wave speed was determined by the ratio of pressure to density in the plasma, which physics predicts precisely based on the universe's temperature and composition. The sound wave stopped propagating abruptly when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms at redshift Z equals 1090, about 380,000 years after the Big Bang. This recombination event released photons that had been trapped, scattering off free electrons. The photons streamed freely through space, creating the cosmic microwave background we observe today. Simultaneously, the sound waves froze. They could not propagate through neutral gas the way they propagated through plasma. The density fluctuations at that moment became imprinted in the distribution of matter. The characteristic scale of these frozen sound waves is about 150 megaparsecs, roughly 490 million light-years in today's universe. This is the distance sound waves travelled in the plasma before recombination, often called the sound horizon at recombination. Regions separated by this distance show enhanced correlation in their density. There are slightly more galaxy pairs separated by 150 megaparsecs than at other separations. This excess shows up as a peak in the galaxy correlation function, a statistical measure of how galaxy positions relate. The Sloan Digital Sky Survey first detected this peak conclusively in 2005 by measuring positions of 46,748 luminous red galaxies. The data showed a clear bump in the correlation function at approximately 150 megaparsecs. This detection confirmed theoretical predictions and provided a standard ruler, an object of known size that can be used to measure distances. Because physics determines the sound horizon size at recombination, observing its apparent size at different distances reveals how much the universe has expanded. The technique works like this. Measure the sound horizon's apparent size in galaxy distributions at various redshifts. Nearby structures appear large in the sky. Distant structures appear small. But the relationship between apparent size and distance depends on the universe's expansion history. If expansion is accelerating, distant structures appear larger than they would in a non-accelerating universe. By measuring the apparent size at multiple distances, astronomers map the expansion history and constrain dark energy's properties. The Baryon Oscillation Spectroscopic Survey, BOSS, completed in 2014, measured galaxy positions for 1.5 million galaxies across a quarter of the sky. The analysis revealed the Baryon acoustic oscillation peak with unprecedented precision. The measurement uncertainty dropped below 1%, making this one of cosmology's most precise measurements. The data confirmed that the universe's expansion is accelerating, driven by dark energy comprising roughly 68% of the total energy density. The Dark Energy Spectroscopic Instrument, DESI, which began operations in 2021, is pushing measurements further. Over 5 years, DESI will map 35 million galaxies and 2.4 million quasars, measuring their positions and distances through spectroscopy. This immense dataset will measure the baryon acoustic oscillation scale at multiple cosmic epochs with exquisite precision, tracing dark energy's behavior across 11 billion years of cosmic history. Early results released in 2024 have already improved upon previous measurements. The connection to the mirror universe appears in how baryon acoustic oscillations constrain cosmic geometry and composition. The mirror universe model predicts specific relationships between ordinary matter density, dark matter density, and dark energy density. These predictions must match observations of the baryon acoustic oscillation scale. If ordinary matter in the mirror universe contributes to dark matter in our universe through gravitational coupling, the total matter density should equal twice the ordinary matter density in each individual universe. Current measurements show that ordinary matter comprises about 5% of the universe's total energy density. Dark matter comprises about 27%, and dark energy comprises about 68%. The mirror universe model requires dark matter density to be approximately equal to ordinary matter density in both universes combined. This means each universe should contain about 13.5% dark matter from the other universe, plus 5% ordinary matter visible within that universe. The ratio matches observations reasonably well, though precise measurements continue refining these numbers. Baryon acoustic oscillations also constrain the universe's spatial curvature. If space curves positively, like a sphere's surface, the apparent size of the sound horizon would differ from expectations in flat space. If space curves negatively like a saddle, the apparent size would differ in the opposite direction. Measurements show the universe is flat to within 0.4%. The sound horizon's apparent size matches the prediction for flat geometry. The mirror universe model requires flatness because CPT symmetry naturally produces zero curvature. The observations confirm this prediction. The sound horizon scale depends on the universe's expansion rate before recombination. During this era, the expansion was controlled by radiation and matter densities. The sound speed in the plasma depends on the ratio of photon pressure to matter inertia, which depends on the baryon to photon ratio. This ratio is measured independently from the cosmic microwave background and from Big Bang nucleosynthesis. The formation of light elements in the first few minutes. All three measurements agree, confirming our understanding of the early universe. In the CPT symmetric cosmology, both universes undergo identical expansion histories from their respective Big Bangs forward in their own time directions. Both produce baryon acoustic oscillations with the same characteristic scale. The sound waves in our universe and the mirror universe propagate symmetrically. When we observe galaxy clustering in our universe, showing the 150 megaparsec scale, the mirror universe's galaxy clustering should show the identical scale. This symmetry is built into the model's structure. Future surveys will measure baryon acoustic oscillations with percent-level precision across most of cosmic history. The Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will survey hundreds of millions of galaxies, measuring their positions spectroscopically. The European Space Agency's Euclid mission, launched in 2023, is simultaneously mapping galaxy positions across billions of years. Both missions will measure the baryon acoustic oscillation scale as a function of redshift, tracing dark energy's evolution with unprecedented detail. These measurements will test whether dark energy's density remains constant or changes over time. If dark energy density increases, the expansion rate accelerates faster, affecting the apparent size of the baryon acoustic oscillation scale at different distances. If dark energy density decreases, expansion accelerates more slowly. The CPT symmetric cosmology makes specific predictions. Dark energy should remain constant because symmetry constrains its value. Any detection of dark energy evolution would challenge the mirror universe model. Baryon acoustic oscillations provide completely independent confirmation of results from supernovae and cosmic microwave background measurements. The three methods use different physics, different observations, and different systematic errors, yet all three agree: the universe is accelerating, dark energy dominates, and space is flat. This concordance strengthens confidence in the standard cosmological model. Any deviation would be revolutionary. The mirror universe model must match all three measurements simultaneously, providing tight constraints on its parameters. Gravitational lensing maps. Light bends around massive objects. This gravitational lensing, predicted by Einstein's general relativity and confirmed in 1919 during a solar eclipse, has become one of astronomy's most powerful tools. By measuring how light from distant galaxies distorts around foreground mass concentrations, astronomers map the distribution of all matter, both visible and dark, across the universe. These maps reveal the cosmic web's structure, test theories of gravity, and provide independent measurements of dark matter that complement other observations. The technique directly tests whether dark matter behaves as the mirror universe model predicts. Gravitational lensing occurs because mass curves spacetime. Light follows the straightest possible paths through curved spacetime paths called geodesics. When light passes near a massive object, like a galaxy cluster, space-time curvature deflects the light's trajectory. The deflection angle depends on the mass distribution. More mass produces stronger curvature and greater deflection. By measuring deflection angles for light from many background galaxies, astronomers reconstruct the foreground mass distribution. There are three modes of lensing. Strong lensing produces multiple images of a single background galaxy, or distorts it into arcs and rings. This occurs when light passes very close to massive foreground objects, like galaxy clusters. The iconic Hubble Space Telescope images of galaxy clusters show spectacular examples: background galaxies stretched into luminous arcs, wrapping around the cluster center. These arcs are actually single galaxies whose light has traveled multiple paths around the cluster, creating distorted images. Weak lensing produces subtle distortions in galaxy shapes. Individual galaxies appear slightly elongated, stretched tangentially around foreground mass concentrations. The distortion is typically only 1%, far too small to notice by eye. But by measuring shapes of millions of galaxies, statistically, astronomers detect the systematic pattern of distortions. This reveals mass distributions even when no strong lensing occurs, mapping dark matter across the entire sky. Microlensing involves objects of smaller mass stars, planets, or compact objects like black holes. When a foreground object passes directly in front of a background star, lensing temporarily brightens the background star as the foreground object's gravity focuses its light. The brightening lasts days to months depending on the object's mass and velocity. Microlensing surveys search for these events, discovering planets around distant stars and constraining how much dark matter could consist of compact objects. The first gravitational lens system was discovered in 1979 by Dennis Walsh, Bob Carswell, and Ray Wayman. They observed a quasar, a brilliantly luminous distant galaxy that appeared as two images separated by 6 arcseconds. Spectroscopy showed both images had identical spectra and redshifts. They were not two quasars, but two images of one quasar, gravitationally lensed by a foreground galaxy. This discovery proved that gravitational lensing occurs in nature and opened a new field of observational astronomy. Hundreds of strong lens systems are now known. The largest surveys have found thousands of galaxy-galaxy lenses and dozens of spectacular cluster lenses. The Hubble Space Telescope's deep surveys of galaxy clusters revealed their power as gravitational telescopes. They magnify background galaxies, allowing observations of objects too faint to detect otherwise. In 2022, the James Webb Space Telescope used cluster lensing to observe the most distant galaxy known, seen as it was just 320 million years after the Big Bang. Weak lensing surveys map dark matter across cosmic scales. The Canada-France-Hawaii Telescope Legacy Survey, completed in 2008, measured shapes of 57 million galaxies across 154 square degrees of sky. The analysis revealed dark matter's distribution, showing that it forms a cosmic web, filaments and sheets connecting galaxy clusters with vast voids between. The dark matter distribution closely mirrors the galaxy distribution, confirming that galaxies form in dark matter halos. The Dark Energy Survey, conducted from 2013 to 2019, mapped 300 million galaxies across 5,000 square degrees. The weak lensing analysis measured mass concentrations across redshifts from 0.2 to 1.3, covering the past 8 billion years. The results showed how structure has grown over time, testing whether gravity behaves as general relativity predicts on cosmic scales. The data confirmed Einstein's theory to high precision. No significant deviations appeared. The Vera Rubin Observatory, which began operations in 2024, will revolutionize weak lensing measurements. Over 10 years, it will observe the entire southern sky every few nights, measuring shapes of billions of galaxies. The immense dataset will map dark matter's three-dimensional distribution across most of cosmic history. The statistical errors will drop by factors of 10 compared to previous surveys, enabling tests of gravity and dark energy with unprecedented precision. Gravitational lensing tests whether dark matter interacts only through gravity or whether it has additional interactions. If dark matter particles collide with each other, self-interacting dark matter, the collisions would smooth out small-scale structure. Dark matter halos would have flatter central density profiles than predicted by gravity-only simulations. Lensing observations measure these density profiles directly by fitting how they deflect background light. Current measurements show dark matter behaves as the mirror universe model predicts. Dark matter appears collisionless. Particles pass through each other without scattering. This matches expectations if dark matter consists of ordinary matter in the mirror universe. Mirror universe particles cannot collide with each other across the singularity boundary. They interact gravitationally with our universe, but have no particle interactions within our universe. Lensing observations confirm this collisionless behavior. The bullet cluster, observed in detail by the Chandra X-ray Observatory and Hubble Space Telescope, provides striking evidence for dark matter's existence and properties. This system consists of two galaxy clusters that collided about 150 million years ago. The hot gas in each cluster, visible in X-rays, slowed and compressed during the collision, remaining between the clusters. But the galaxies themselves and the dark matter passed through with minimal interaction. Gravitational lensing maps show the mass concentration dark matter is offset from the gas, proving dark matter exists and is collisionless. The mirror universe model predicts this exact behavior. Ordinary matter, stars, gas, and galaxies interacts electromagnetically and can collide. Mirror universe matter, manifesting as dark matter in our universe, does not interact electromagnetically and cannot collide with itself across the singularity. During cluster mergers, visible matter slows through collisions and pressure, but dark matter continues unimpeded. The bullet cluster observations precisely match these predictions. Lensing also tests alternative gravity theories. Modified Newtonian dynamics, MOND, and related theories attempt to explain galaxy rotation curves without dark matter by modifying gravity at low accelerations. But these theories struggle with gravitational lensing. Lensing depends on total mass, whether that mass consists of particles or not. To explain lensing observations without dark matter, modified gravity theories must produce stronger gravitational fields than the visible matter warrants. This requires invoking unseen matter, defeating the purpose of avoiding dark matter. The mirror universe model has no such problem. It predicts dark matter is ordinary matter in the mirror universe, gravitationally coupled to our universe. Gravitational lensing measures this mass directly. The amount of lensing should equal the combined mass of visible matter in our universe plus visible matter in the mirror universe. Observations show roughly 5 times more mass than visible in our universe alone. If mirror universe matter contributes equally, the total is twice the ordinary matter, still less than observed, but in the right range considering dark energy and measurement uncertainties. Cosmic void structure. The universe resembles Swiss cheese. Galaxies cluster into filaments and sheets surrounding enormous empty regions called cosmic voids. These voids span 50 to 150 megaparsecs, up to 500 million light-years, and contain far fewer galaxies than average. They occupy most of space, with galaxies concentrated in the walls between voids. Understanding void structure reveals how gravity and expansion compete to shape cosmic structure. The voids themselves provide crucial tests of dark energy, modified gravity theories, and the mirror universe hypothesis. Cosmic voids were discovered gradually as galaxy surveys expanded. In 1978, Stephen Gregory and Laird Thompson identified the first void, a region in Boötes containing no bright galaxies within a 150 million light-year diameter. Initial skepticism gave way to acceptance as more voids appeared in surveys. The CFA Redshift survey in the 1980 mapped thousands of galaxies, revealing that voids are common, not rare. About 60% of space is in voids, with galaxies concentrated in the remaining 40%. Voids form through gravitational instability running backward. In regions slightly less dense than average, gravity pulls matter outward towards surrounding denser regions. As matter flows out, the void becomes emptier, and its expansion accelerates relative to the cosmic average. The void's expansion isn't true expansion, it's differential motion as matter moves toward higher density regions. But from within the void, it looks like expansion. Galaxies on opposite sides of a void recede from each other faster than the Hubble expansion would predict based on distance alone. The largest known void is the Eridanus supervoid, spanning approximately 1 billion light-years. It contains roughly 10,000 fewer galaxies than expected for a typical region of that size. Discovered through the cosmic microwave background, this void creates a cold spot, a region slightly cooler than surrounding areas. Photons passing through the void experience the integrated Sachs-Wolf effect. They gain energy falling into the void and lose energy climbing out. If expansion is accelerating, the void grows deeper during the photon's transit, causing a net energy loss and temperature decrease. The local void lies just 150 million light-years from the Milky Way. We sit on its edge, on a filament separating it from neighbouring voids. The local void spans about 150 million light-years and contains only about 60 known galaxies, far fewer than the thousands expected in a typical region. Our position on the void's edge affects observations. The matter between us and the void's interior flows toward us, affecting measurements of the local expansion rate. Void statistics constrain dark energy and gravity. In a universe dominated by dark energy, voids expand faster than in a matter-dominated universe. The size distribution of voids, how many small, medium, and large voids exist, depends sensitively on dark energy's properties. Surveys measuring this distribution test whether dark energy density remains constant or changes over time. Modified gravity theories also predict different void properties than general relativity, making voids powerful discriminators between theories. The Sloan Digital Sky Survey identified over 1,000 voids using various algorithms. Different methods define voids differently, but all find similar statistical properties. The void probability function, the probability of finding a sphere of radius r containing few or no galaxies, follows predictions from gravitational instability theory. Voids grow as matter falls out of them, but their growth slows as dark energy's influence increases at late times. Galaxy velocities in voids test gravity. Galaxies near void centers should move outward as they fall toward the void walls. Measuring these peculiar velocities, motions relative to smooth Hubble expansion, reveals the gravitational potential. In general relativity with dark matter, the velocities should match predictions from the matter distribution. Modified gravity theories often predict different velocity patterns. The mirror universe model predicts velocities consistent with general relativity plus dark matter from the mirror universe's gravitational influence. Observed velocities match general relativity's predictions. Galaxies near void centers move outward at speeds of 100 to 300 kilometers per second, exactly as predicted from the surrounding matter distribution, assuming standard gravity and dark matter. No evidence appears for modified gravity effects. This agreement supports the mirror universe model, which uses standard gravity with dark matter from the mirror universe, rather than modified gravity theories that attempt to explain observations without dark matter. Void shapes provide another test. If gravity behaves as Einstein predicted, voids should be roughly spherical or slightly elongated along the filaments connecting them. Modified gravity theories sometimes predict different shapes, more elongated or more clustered. Observations show voids are indeed roughly spherical with moderate ellipticity, matching general relativity's predictions. The distribution of shapes follows predictions from simulations including standard gravity and dark matter. The Alcock-Paczynski test uses void shapes to measure cosmic geometry. This geometric test compares a void's apparent size perpendicular to the line of sight with its size along the line of sight. The ratio depends on how the universe expands. Different expansion histories produce different size ratios. By measuring this ratio for many voids at different distances, astronomers constrain dark energy's properties and the universe's curvature. The method is independent of galaxy properties, depending only on geometry. Results from the Alcock-Paczynski test using voids agree with other measurements. The universe is flat or very nearly flat. Spatial geometry is Euclidean on large scales. Dark energy comprises about 68% of the total energy density. The equation of state parameter W, the ratio of dark energy's pressure to its density, is consistent with -1, the value for a cosmological constant. These results align with the mirror universe model's prediction of a constant vacuum energy arising from CPT symmetry requirements. Void dynamics evolve with cosmic time. At early times when matter dominated, voids grew primarily through matter flowing out as galaxies formed in overdense regions. As dark energy became important within the past few billion years, void expansion accelerated. Future observations with larger surveys will measure how void sizes and numbers change with redshift, tracing this evolution across cosmic history. The mirror universe model predicts specific evolution rates based on CPT symmetric dark energy. The Cosmic Void Catalogue from the Sloan Digital Sky Survey contains detailed properties of over 1,000 voids, positions, sizes, shapes, and the numbers and types of galaxies they contain. This catalogue enables statistical tests of cosmological models. Researchers compare observed void properties with predictions from simulations. The match is excellent for simulations including dark matter and dark energy, with properties matching other observations. Alternative models without dark matter or with modified gravity produce void distributions that don't match observations. Small galaxies inhabit void interiors. These void galaxies differ from galaxies in denser regions. They tend to be bluer, indicating active star formation. They are more gas-rich, having retained their gas without interactions that strip it away. They are less clustered, often isolated in space. Studying void galaxies reveals how environment affects galaxy evolution. The mirror universe's gravitational influence should affect void galaxies identically to galaxies in filaments. No difference is predicted based on location. Future surveys will map voids across cosmic time. The Dark Energy Spectroscopic Instrument will measure galaxy positions and velocities for tens of millions of galaxies, identifying voids at redshifts up to 2 looking back 10 billion years. The Nancy Grace Roman Space Telescope will complement these measurements with high-resolution imaging. Together, they will reveal how the void network evolved as dark energy came to dominate the universe's expansion. Neutrino mass hierarchy and CPT implications. Neutrinos possess mass, but determining their mass hierarchy remains one of particle physics' outstanding puzzles. These nearly massless particles come in 3 flavors: electron, muon, and tau neutrinos, and oscillate between flavors as they travel. The mass differences between flavors have been measured through oscillation experiments, but whether the heaviest neutrino is the 3rd or 1st generation remains unknown. This hierarchy question connects to the mirror universe through CPT symmetry requirements that constrain neutrino properties in both universes. Neutrino oscillations were discovered through measurements of solar neutrinos in the 1960s. Ray Davis's pioneering experiment detected only 1/3 the expected electron neutrinos from the Sunday. This solar neutrino problem persisted for decades until physicists realized neutrinos change flavor during their journey. Electron neutrinos produced in the Sun's core oscillate into muon and tau neutrinos before reaching Earth. Davis's detector only captured electron neutrinos, missing the others. The oscillation probability depends on mass differences between neutrino types. quantum mechanics allows particles to exist as superpositions of different mass states. A neutrino produced as an electron neutrino is actually a mixture of three mass states. As it propagates, these states acquire different quantum phases proportional to their masses. After traveling some distance, the superposition can correspond to a muon or tau neutrino. The oscillation length distance between flavor conversions depends on the mass differences and the neutrino's energy. Measurements reveal two mass splittings. The solar mass splitting, measured through solar neutrinos and reactor experiments, is approximately 0.000075 electron volts squared. The atmospheric mass splitting, measured through atmospheric neutrinos and accelerator experiments, is about 0.0025 electron volts squared. These splittings are extraordinarily small. Neutrinos are at least 1 million times lighter than electrons. But the ordering remains ambiguous. Are the masses arranged as M1 is less than, M2 is less than, M3 normal hierarchy, or M3 is less than, M1 is less than, M2 inverted hierarchy? The normal hierarchy would mean the heaviest neutrino is the tau neutrino's dominant component. The inverted hierarchy would make the electron and muon neutrinos' dominant components heavier than the tau neutrinos. Determining which hierarchy describes nature requires measuring how neutrinos and antineutrinos oscillate differently. CPT symmetry relates particles to antiparticles. If CPT is exact, neutrinos and antineutrinos should have identical masses and opposite oscillation phases. Any difference would indicate CPT violation. The mirror universe model requires CPT symmetry to be exact. The two universes are CPT conjugates, charge, parity, and time all flip across the Big Bang singularity. If neutrinos violated CPT symmetry, the mirror universe's neutrinos would behave differently than our universe's neutrinos when accounting for the CPT transformation. This would break the fundamental symmetry underpinning the model. Precise measurements of neutrino oscillations test whether CPT symmetry holds for leptons as it does for quarks. Current experiments searching for the mass hierarchy include the Deep Underground Neutrino Experiment, DUNE, in the United States and Hyper-Kamiokande in Japan. DUNE will send neutrino beams 1,300 kilometers through Earth, from Fermilab to detectors in South Dakota. By comparing oscillation probabilities for neutrinos and antineutrinos at this distance, the experiment will determine the hierarchy and search for CPT violation. Any detected violation would challenge the mirror universe model fundamentally. Hyper-Kamiokande, scheduled to begin operations in 2027, will study atmospheric neutrinos produced by cosmic rays hitting Earth's atmosphere. These neutrinos travel through Earth at various distances depending on their arrival angle. Measuring oscillations as a function of distance and energy will resolve the mass hierarchy. The detector contains 260,000 tons of ultra-pure water, making it 50 times more sensitive than its predecessor, Super-Kamiokande. Neutrino masses themselves constrain cosmology. The sum of all neutrino masses affects how structure forms in the universe. Massive neutrinos move relativistically during structure formation, streaming out of overdense regions and smoothing density fluctuations on small scales. Cosmic microwave background observations and galaxy surveys constrain the total neutrino mass to less than 0.12 electron volts. This upper limit, combined with measured mass splittings, constrains individual neutrino masses. The mirror universe model predicts that mirror neutrinos contribute to the universe's relativistic particle content in the early universe. During Big Bang nucleosynthesis, the expansion rate depended on all relativistic species present. Standard model neutrinos contributed, and mirror neutrinos would add equally. However, if the mirror and regular sectors are thermally decoupled, not exchanging energy, mirror neutrinos don't affect our universe's early expansion. The observed helium abundance limits additional relativistic species, constraining how mirror and regular sectors interact thermally. Cosmological neutrinos form a background filling the universe, similar to the cosmic microwave background. These relic neutrinos decoupled from other matter when the universe was 1 second old. Today they have cooled to about 2 degrees above absolute zero. Detecting this cosmic neutrino background remains beyond current technology, but future experiments may succeed. The mirror universe would produce an equivalent neutrino background in its domain, invisible to us, but gravitationally coupled through space-time curvature. Majorana versus Dirac neutrinos represent another open question. Dirac neutrinos, like electrons, are distinct from their antiparticles. Majorana neutrinos are their own antiparticles. A neutrino and antineutrino are the same particle in different states. This distinction affects whether neutrinos can enable neutrinoless double beta decay, where atomic nuclei decay, emitting 2 electrons and no neutrinos. Observing this decay would prove neutrinos are Majorana particles and provide information about absolute neutrino masses. The mirror universe model is compatible with either Majorana or Dirac neutrinos. If neutrinos are Majorana particles, mirror universe neutrinos would also be Majorana particles due to CPT symmetry. The mass generation mechanisms would mirror each other across the singularity. If neutrinos are Dirac particles with separate antiparticles, mirror neutrinos, likewise, have separate antiparticles. Current experiments searching for neutrinoless double beta decay will determine neutrino nature and test whether the mirror universe's neutrino sector matches predictions. Primordial magnetic fields. The universe contains magnetic fields at all scales, from planets and stars to galaxies and galaxy clusters. The origin of these fields, particularly large-scale magnetic fields pervading intergalactic space, remains mysterious. Observations reveal coherent magnetic fields stretching millions of light-years through galaxy clusters. Such fields cannot have formed recently through astrophysical processes alone. Their coherence length exceeds what stellar or galactic dynamos can produce. Understanding primordial magnetic fields may require mechanisms operating in the very early universe, potentially involving physics from the mirror universe model. Magnetic fields in galaxy clusters were discovered through radio observations. Synchrotron radiation from relativistic electrons spiraling in magnetic fields produces radio emission. The strength of this emission reveals field strengths of approximately 1 microgauss throughout clusters weak compared to Earth's magnetic field, but significant for structures hundreds of millions of light-years across. The fields show coherent structure on megaparsec scales, suggesting they formed early or were amplified efficiently from tiny seed fields. Several mechanisms have been proposed for generating primordial magnetic fields. During cosmic inflation, quantum fluctuations of electromagnetic fields could have been stretched to macroscopic scales, creating seed fields. However, standard electromagnetic theory predicts these fields would be negligibly weak, far too small to explain observed strengths, even after billions of years of amplification. Modified electromagnetism during inflation, or new physics coupling inflation to electromagnetism, might generate stronger seeds. Phase transitions in the early universe offer another route. When the universe cooled through critical temperatures, symmetries broke spontaneously. The electro-weak phase transition, occurring when the universe was about 1 picosecond old, might have generated magnetic fields through bubble collisions or turbulence. The quantum chromodynamic phase transition, when quarks confined into protons and neutrons, could similarly produce fields. Calculations suggest these transitions generate fields on small scales that must be amplified later. The mirror universe introduces a novel possibility. If magnetic fields in both universes couple through gravity, primordial fields from the mirror universe could influence structure formation in our universe. During the early universe, when both sectors were hot and dense, electromagnetic fields in each sector would curve space-time. This curvature affects matter in both universes. Magnetic fields in the mirror universe could provide the seed fields needed in our universe, already possessing the required coherence length. Observations constrain primordial magnetic field strength. The cosmic microwave background is sensitive to magnetic fields present at recombination. Strong fields would distort temperature patterns through several effects. The Faraday effect rotates polarization of light passing through magnetized plasma. Magnetic pressure affects plasma dynamics, changing how sound waves propagate. Upper limits from Planck satellite data constrain primordial fields to less than a few nanogauss on megaparsec scales at recombination. These limits challenge some generation mechanisms, while allowing others. Fields produced during inflation are typically below detection thresholds. Phase transition fields on small scales could have amplified to observed strengths through turbulence and dynamo action during structure formation. The mirror universe scenario predicts fields might be at the detection threshold strong enough to seed galaxy cluster fields, but weak enough to satisfy cosmic microwave background constraints. Measuring magnetic fields in cosmic voids tests their primordial origin. If fields formed after structure collapsed through stellar winds, supernovae, and galactic outflows, void regions should be unmagnetized. But observations suggest even voids contain weak fields. Gamma rays from distant blazars travel through intergalactic space and can convert to electron-positron pairs in the presence of magnetic fields. The pairs emit secondary gamma rays, creating a cascade. The arrival pattern of these gamma rays constrains magnetic fields along the path, including through voids. The Fermi Gamma Ray Space Telescope has studied these cascades. Results indicate magnetic fields of at least 10 to the power of -16 Gauss pervade intergalactic space, including voids. This strength is difficult to explain through astrophysical outflows alone, suggesting a primordial origin. The mirror universe model naturally explains ubiquitous weak fields gravitational coupling between mirror and regular electromagnetic sectors, provides seeds everywhere, not just near galaxies. Magnetic field topology provides clues to generation mechanisms. Helical fields, fields with a preferred handedness or chirality, arise naturally from certain phase transitions involving parity violation. Non-helical fields lack this handedness. Measuring helicity through Faraday rotation across many lines of sight would distinguish mechanisms. The mirror universe model predicts that if our universe's fields are helical, mirror universe fields have opposite helicity due to parity inversion across the singularity. Future observations will measure primordial magnetic fields more precisely. The Square Kilometre Array, currently under construction, will observe polarized radio emission from billions of galaxies. Mapping Faraday rotation across the sky reveals magnetic field structure on all scales. The enhanced sensitivity will detect or tightly constrain intergalactic magnetic fields. Comparing observations with predictions from various generation mechanisms, including mirror universe scenarios, will narrow the origin of cosmic magnetism. Dark matter annihilation signatures. If dark matter consists of particles, those particles might annihilate when they collide, producing observable radiation. The galactic center, dwarf galaxies, and galaxy clusters represent prime locations to search for annihilation signals. Telescopes spanning gamma-ray, X-ray, and radio wavelengths scan these regions for excess emission that cannot be explained by conventional astrophysics. The mirror universe model makes specific predictions about whether such signals should exist and their characteristics, differing from typical dark matter particle candidates. Standard dark matter candidates like WIMPs, weakly interacting massive particles, annihilate when particles and antiparticles meet. The annihilation produces standard model particles, quarks, leptons, and gauge bosons. These particles decay or hadronize, ultimately producing stable particles including gamma rays, neutrinos, and cosmic rays. The annihilation rate depends on the dark matter density squared. More encounters occur in denser regions. Galactic centers, with their high dark matter concentrations, should produce strong signals if WIMPs annihilate efficiently. The Fermi Large Area Telescope has searched for gamma-ray signals from dark matter annihilation for over a decade. Observations of the galactic center region show excess gamma-ray emission at giga-electron-volt energies compared to models of known astrophysical sources. This excess could indicate dark matter annihilation, but astrophysical explanations remain viable. Pulsars, rapidly spinning neutron stars, emit gamma rays. An unresolved population of millisecond pulsars concentrated toward the galactic center might explain the excess without dark matter. Dwarf spheroidal galaxies provide cleaner targets. These small galaxies orbiting the Milky Way contain substantial dark matter but few stars and minimal gas. Astrophysical backgrounds are negligible, making them ideal for dark matter searches. Observations of dozens of dwarf galaxies reveal no significant gamma-ray emission above background. This null result constrains dark matter annihilation rates. If WIMPs exist, they annihilate less efficiently than many models predict. The mirror universe model predicts no annihilation signals from standard dark matter searches. Dark matter in our universe consists of ordinary matter in the mirror universe. These are atoms, molecules, and larger structures, not elementary particles. They cannot annihilate with regular matter because they exist across the CPT boundary. Mirror protons remain mirror protons. They do not have antiparticles in our universe to annihilate with. The absence of clear annihilation signals supports the mirror universe interpretation over particle dark matter. Positron excess in cosmic rays has intrigued physicists since measurements by Pamela in 2008 and AMS-02 later. These experiments detected more positrons at high energies than expected from conventional cosmic ray production. Positrons arise when high-energy cosmic rays collide with interstellar gas, producing particle showers. The observed excess might indicate dark matter annihilation, producing electron-positron pairs. Alternatively, pulsars could accelerate positrons efficiently, explaining the excess without dark matter. Recent measurements favor the pulsar explanation. Detailed analysis of positron spectrum, shape, and isotropy matches predictions from nearby pulsar populations. The excess doesn't require dark matter annihilation. The mirror universe model is consistent with this conclusion. It predicts no excess from dark matter annihilation, matching observations once astrophysical sources are properly accounted for. Neutrino telescopes search for dark matter annihilation in the Sun and Earth. Dark matter particles should accumulate in these bodies through gravitational capture, reaching high densities in their cores. If WIMPs annihilate, they would produce neutrinos that escape and travel to detectors. IceCube, a cubic kilometer neutrino detector at the South Pole, searches for such signals. No excess neutrinos from the Sun or Earth have been detected, constraining WIMP properties. These null results are natural in the mirror universe framework. Mirror atoms captured by the Sun or Earth remain mirror atoms. They don't annihilate into neutrinos. The gravitational potential of ordinary matter captures mirror matter, increasing its density in stellar and planetary cores. But no annihilation occurs because CPT symmetry prevents interactions that would produce standard model particles detectable by our instruments. Indirect detection searches will continue with increasing sensitivity. The Cherenkov telescope array under construction will observe gamma rays with unprecedented precision. It will study the galactic center, dwarf galaxies, and galaxy clusters, searching for spectral features indicating dark matter annihilation. Definitive detection would rule out the mirror universe model as formulated. Continued null results would support mirror matter over particle dark matter, though they cannot prove the mirror universe exists. Quantum entanglement across the singularity. Quantum entanglement, the phenomenon where particles share quantum states instantaneously across arbitrary distances, raises profound questions when applied to a CPT symmetric universe. If the mirror universe is our universe's CPT conjugate, quantum states in one universe might be entangled with states in the other. This would establish correlations across the Big Bang's singularity, potentially observable through subtle effects on quantum measurements. While highly speculative, exploring these possibilities reveals how quantum mechanics and cosmology intersect in the mirror universe framework. Entanglement emerges from quantum superposition. When two particles interact, their quantum states become correlated. Measuring one particle's property instantly determines the other's corresponding property, regardless of separation. Einstein called this spooky action at a distance, believing it revealed quantum mechanics' incompleteness. But experiments confirmed entanglement is real. Quantum mechanics is complete, but profoundly non-local. Bell's theorem, proved in 1964, showed that no local hidden variable theory can reproduce quantum mechanics predictions. John Bell derived inequalities that local theories must satisfy. Quantum entanglement violates these inequalities. Experiments testing Bell's inequalities consistently confirm violations, proving entanglement cannot be explained by classical correlations. The universe contains genuine quantum non-locality. CPT symmetry relates particles to antiparticles with reversed charges, parities, and time directions. In quantum field theory, particles and antiparticles are related through CPT transformation. If the mirror universe is the CPT conjugate of our universe, every particle in our universe corresponds to a particle in the mirror universe undergoing the CPT transformation. This correspondence might extend to quantum states. Particles here could be entangled with their CPT conjugates there. Such entanglement would be fundamentally different from ordinary entanglement. Ordinary entangled particles exist within the same universe, sharing a common spacetime. Cross-singularity entanglement would involve particles in distinct spacetime regions connected only at the Big Bang. Information couldn't travel between them through normal spacetime paths. Yet quantum correlations might persist, established at the Big Bang when the universes were connected. Testing this hypothesis faces enormous challenges. We cannot directly observe the mirror universe or exchange particles with it. Any entanglement correlations would manifest indirectly through subtle effects on quantum measurements in our universe. Deviations from standard quantum mechanics predictions might indicate cross-singularity entanglement. No such deviations have been observed, but experiments haven't specifically targeted this possibility. One proposal involves cosmological Bell tests. Instead of entangling particles in a laboratory, use particle pairs created in the early universe. Cosmic microwave background photons from opposite sides of the sky were once in causal contact during inflation. they might be entangled. Measuring their polarizations could test Bell inequalities on cosmological scales. If cross-singularity entanglement exists, additional correlations beyond standard predictions might appear. Another approach examines quantum vacuum fluctuations. The quantum vacuum contains virtual particle-antiparticle pairs constantly forming and annihilating. In the mirror universe picture, virtual particles in our universe might correlate with virtual particles in the mirror universe through CPT symmetry. This could subtly affect vacuum energy calculations. The cosmological constant problem why vacuum energy is so small might relate to cancellations from cross-singularity quantum correlations. Critics argue that entanglement across the singularity contradicts causality. If the universes are truly separate, no information can propagate between them. Entanglement doesn't transmit information measuring. One particle doesn't send signals to the other, but establishing entanglement requires initial causal contact. At the Big Bang, perhaps both universes were causally connected, allowing entanglement formation. As they separated, correlations persisted while causal connections severed. Quantum mechanics on curved spacetime provides the theoretical framework. General relativity describes spacetime geometry dynamically. Quantum field theory on this curved background treats particle creation and vacuum states carefully. The Big Bang singularity represents an extreme environment where both quantum effects and gravitational effects are strong. Proper treatment requires quantum gravity, a theory not yet fully developed. Speculations about cross-singularity entanglement await this theory's completion. Cosmic dawn and the mirror universe's stars. The cosmic dawn, when the first stars ignited, marks a pivotal transition from the universe's dark ages to the era of galaxies. These primordial stars, called population 3 stars, formed from pristine hydrogen and helium with no heavier elements. Their light reionized the intergalactic medium, making the universe transparent to ultraviolet radiation. Understanding cosmic dawn tests cosmological models, including the mirror universe hypothesis. If a mirror universe exists, its own cosmic dawn occurs simultaneously, and subtle gravitational effects from mirror universe stars might influence structure formation in our universe. Population 3 stars have never been directly observed. They formed when the universe was between 100 and 400 million years old at redshifts of 20 to 30. These stars were massive, perhaps 100 to 1,000 solar masses, and extremely hot. Their ultraviolet radiation was intense, capable of ionizing hydrogen across vast distances. They lived briefly, only a few million years, before exploding as supernovae. These explosions synthesized and dispersed heavy elements, enriching the gas that formed subsequent stellar generations. The James Webb Space Telescope is searching for population 3 stars by observing the early universe. Its infrared detectors can detect light from galaxies at redshifts exceeding 10, corresponding to when the universe was less than 500 million years old. Early results have identified candidate galaxies at these epochs, some containing stars that might be population 3 or very metal poor. Confirming zero metallicity requires spectroscopy, revealing the absence of heavy element absorption lines. Cosmic dawn affected the universe's ionization state. Before the first stars formed, intergalactic hydrogen was neutral. Starlight ionized this hydrogen through photoionization photons with energies exceeding 13.6 electron volts, strip electrons from hydrogen atoms. As ionized regions grew around star-forming galaxies, they eventually overlapped, completing reionization. Observations of distant quasars show the intergalactic medium became fully ionized by redshift 6, about 1 billion years after the Big Bang. The 21 centimeter line of neutral hydrogen traces reionization. Neutral hydrogen emits radiation at a wavelength of 21 centimeters when its electron spin flips. This emission, redshifted by cosmic expansion, appears at meter wavelengths for hydrogen at cosmic dawn. Radio telescopes detect this signal, mapping neutral hydrogen's distribution across redshifts. Experiments like HERA and the Square Kilometre Array aim to observe the 21 centimeter signal from cosmic dawn, revealing when and how reionization occurred. The mirror universe underwent its own cosmic dawn. CPT symmetry requires identical processes in both universes, just time reversed relative to each other. Mirror universe population 3 stars, formed at the same cosmic time, reionized mirror universe gas and enriched it with heavy elements. These processes unfolded identically in both domains. Gravitationally, mirror stars contributed to the total mass density, affecting structure growth rates equally in both universes. Gravitational effects from mirror universe structures influence our universe's evolution. During cosmic dawn, dark matter halos in our universe contained mass from both visible and mirror sectors. The additional mass deepened gravitational potential wells, accelerating gas infall and star formation. This could shift cosmic dawn earlier than predictions without the mirror universe. Conversely, it might affect reionization's topology, the pattern of ionized and neutral regions, if structure formation details differ due to additional mass. Current observations don't yet constrain these effects precisely. The 21 centimeter signal has not been definitively detected from cosmic dawn. When detected, its amplitude and structure will reveal reionization's timing and morphology. Comparing observations with simulations including only visible matter versus simulations including mirror universe mass will test whether the mirror universe's presence is necessary to match data. Discrepancies might indicate additional physics beyond standard cosmology. Supernova feedback from population 3 stars shaped subsequent star formation. These massive stars' deaths released enormous energy, heating, gas, and driving it out of small galaxies. This feedback regulated star formation rates, preventing runaway conversion of gas to stars. Mirror universe supernovae similarly affected mirror universe structure, but also influenced our universe gravitationally. The combined feedback from both sectors might explain observed star formation efficiencies in early galaxies. Future observations will probe cosmic dawn with unprecedented detail. The Nancy Grace Roman Space Telescope will image early galaxies, identifying candidates for population 3 stars through their unique spectral properties. Ground-based 21 centimeter arrays will map neutral hydrogen across cosmic dawn, revealing reionization's progression. These observations will test whether structure formation proceeded faster or slower than predictions, potentially revealing mirror universe influences. The cosmic neutrino background. Hidden throughout space is a sea of neutrinos left over from the Big Bang, the cosmic neutrino background. These relic neutrinos formed 1 second after the universe began, when temperatures dropped below 10 billion degrees and neutrinos decoupled from matter. Since then, they have travelled freely through space, cooling as the universe expands. Today, theory predicts about 330 neutrinos per cubic centimetre fill the universe, outnumbering atoms by roughly 1 billion to 1. Detecting these relic neutrinos would provide a direct window into the universe's first, second, and test whether the mirror universe contributes an equal neutrino population. The cosmic neutrino background parallels the cosmic microwave background, but formed earlier and at higher temperatures. In the first microsecond after the Big Bang, neutrinos were in thermal equilibrium with electrons, positrons, and photons through weak interactions. Neutrinos scattered frequently off these particles, maintaining the same temperature. As the universe expanded and cooled, the weak interaction rate dropped. At about 1 second, when temperature fell to 10 billion degrees, neutrinos decoupled, they stopped interacting and began free streaming through space. This decoupling established the neutrino temperature relative to the photon temperature. After neutrinos decoupled, electrons and positrons annihilated into photons, slightly reheating the photon bath, but not the decoupled neutrinos. The reheating factor is 11/4, 1/3, meaning today's neutrinos should be cooler than photons by this factor. The cosmic microwave background temperature is 2.725 Kelvin, so the cosmic neutrino background temperature should be about 1.95 Kelvin. This corresponds to typical neutrino energies around 0.00017 electron volts. Extraordinarily small, detecting individual relic neutrinos is impossibly difficult with current technology. These ultra-low energy neutrinos interact even more weakly than the energetic neutrinos from the sun or nuclear reactors that experiments routinely detect. The capture cross-section, the probability a neutrino interacts with matter, is proportional to neutrino energy. Relic neutrinos have energies 1 billion times smaller than solar neutrinos, making their interactions 1 billion times rarer. No conceivable detector could capture enough relic neutrinos to measure directly. But the cosmic neutrino background affects cosmological observables even if individual neutrinos cannot be detected. The neutrino energy density contributes to the universe's total energy budget, affecting expansion rate history. During the radiation-dominated era before matter domination, neutrinos provided about 40% of the total radiation density. The rest came from photons and electron-positron pairs. This neutrino contribution is essential for correctly predicting Big Bang nucleosynthesis outcomes, like helium and deuterium abundances. The number of neutrino species affects nucleosynthesis timing crucially. More neutrino types mean higher radiation density, faster expansion, and earlier freeze-out of nuclear reactions. This leaves more neutrons available for helium formation, increasing the helium-4 abundance. Comparing observed primordial abundances with predictions constrains the effective number of neutrino species to be 3, plus or minus 0.3. The standard model predicts exactly 3 species: electron, muon, and tau neutrinos. Agreement between theory and observation confirms our understanding of the early universe and constrains exotic physics that might add extra species. The Planck satellite measured cosmic microwave background fluctuations with exquisite precision, enabling independent determination of the effective neutrino number through subtle effects on the microwave background spectrum. Neutrinos affect the expansion rate during recombination when the microwave background is formed, changing the sound horizon scale that baryon acoustic oscillations measure. Planck's analysis yielded an effective neutrino number of 3.04 plus or minus 0.18, consistent with 3 standard neutrinos and ruling out large populations of additional neutrino-like particles. In a CPT symmetric cosmology with a mirror universe, the cosmic neutrino background should exist in both universes. Our universe contains 3 neutrino flavors at temperature 1.95 Kelvin. The mirror universe contains 3 mirror neutrino flavors at the same temperature in its frame. From our perspective, mirror neutrinos exist but don't interact with our matter through electromagnetic or weak forces, only through gravity. They contribute to the total neutrino energy density affecting cosmological expansion. If mirror neutrinos are massive, their contribution to dark matter depends on their masses. Current constraints suggest standard neutrinos have masses below 0.12 electron volts, too light to constitute dark matter. If mirror neutrinos have identical masses due to CPT symmetry, they also cannot be dark matter. But if neutrinos have unexpected heavy flavors, a fourth species, or heavier mass hierarchy, the relic abundance could contribute significantly. The mirror universe model doesn't require heavy neutrinos. Predicting dark matter comes from mirror atoms rather than mirror neutrinos. Gravitational effects of the cosmic neutrino background might be detectable through clustering measurements. Neutrinos today are non-relativistic if their masses exceed about 0.001 electron volts. Non-relativistic neutrinos cluster gravitationally like dark matter, but they move faster due to thermal velocities from the Big Bang. This hot dark matter component creates distinctive patterns in large-scale structure, suppressing small-scale clustering while following the cosmic web on large scales. The most promising detection method involves measuring how cosmic structure growth is affected by neutrino mass. Massive neutrinos suppress the growth rate of density fluctuations because they stream freely out of collapsing regions. Observations of galaxy clustering at different cosmic epochs should reveal this suppression if neutrino masses are large enough. Current surveys constrain neutrino masses to the range that oscillation experiments predict, but definitive detection of the mass through cosmology requires more precise measurements from upcoming surveys like DESI and Euclid. Another indirect probe uses large-scale velocity flows. Neutrinos contribute to the gravitational potential driving galaxy motions, but their streaming prevents them from clustering tightly. This creates small differences between the distribution of matter clusters, dark matter and atoms, and the total gravitating mass, including smoothly distributed neutrinos. Peculiar velocity surveys, measurements of galaxy motions relative to smooth expansion, could detect these differences if precision improves sufficiently. The mirror universe model makes a specific prediction. The combined neutrino energy density from both universes should equal twice the density of neutrinos in either universe alone. Assuming CPT symmetry ensures identical properties, observations measuring the total neutrino energy density through expansion rate effects test this prediction. Current measurements agree with standard cosmology's 3-neutrino prediction, suggesting mirror neutrinos either don't contribute to our expansion rate, implying they're truly decoupled, or contribute in exactly the predicted way if gravitational coupling occurs. Future neutrino telescopes might detect the cosmic neutrino background indirectly through its effect on ultra-high-energy cosmic neutrinos. When high-energy neutrinos from astrophysical sources propagate through the cosmic neutrino background, they can scatter off background neutrinos, slightly attenuating the flux. This is analogous to how gamma rays interact with the cosmic microwave background. The effect is tiny, requiring enormous neutrino telescopes like IceCube Gen 2, a proposed cubic kilometer detector in Antarctic ice, to detect statistically. Direct detection of relic neutrinos would revolutionize cosmology and particle physics. It would confirm the Big Bang model's prediction that neutrinos decoupled at 1 second test neutrino properties in regimes inaccessible to laboratories, and potentially reveal unexpected physics. The mirror universe model predicts that such detection would show exactly 3 neutrino flavors, with properties matching the standard model, confirming CPT symmetry. Any deviation, extra species, wrong temperature, or unusual interactions would challenge the model and demand new physics beyond the mirror universe framework. Primordial black holes as dark matter candidates. Could dark matter be primordial black holes? Black holes formed in the universe's first moments rather than from collapsing stars. This provocative idea has attracted renewed interest as a potential solution to the dark matter mystery. Primordial black holes could form from density fluctuations in the very early universe, creating gravitating objects that interact only through gravity, matching dark matter's observational properties. Whether they could account for all dark matter, or whether mirror universe matter provides a better explanation, depends on stringent observational constraints from gravitational lensing, gravitational waves, and cosmic structure. Primordial black holes differ fundamentally from stellar black holes. Stellar black holes form when massive stars exhaust their nuclear fuel and collapse under gravity, a well-understood process producing black holes with masses from about 5 to 100 solar masses. Primordial black holes formed in the first second after the Big Bang from regions where density fluctuations exceeded a critical threshold. When a region's density contrast reached about 50% above average, it collapsed directly into a black hole without forming a star first. The mass of a primordial black hole depends on when it formed. Black holes forming at 1 microsecond after the Big Bang would have masses around 10, -8 solar masses, about 10-25 kilograms, roughly Earth's mass. Those forming at 1 second would have roughly 1 solar mass. Later formation times produce proportionally larger masses. The formation time window extends from about 10, -23 seconds, when quantum gravity effects become important, to roughly 1 second, when the universe becomes too uniform for significant overdensities to exist. Stephen Hawking famously showed in 1974 that black holes evaporate through quantum radiation. The evaporation rate depends inversely on mass. Smaller black holes evaporate faster. Black holes, smaller than about 10-15 grams, would have already evaporated by today, having lifetimes shorter than the universe's age. This sets a lower mass limit for primordial black holes that could constitute dark matter. Only those with masses above about 10-15 grams, roughly an asteroid's mass, survive to the present day. The mass range between 10-15 grams and 10-25 grams faces the tightest constraints. Observations of neutron stars have detected no anomalous heating from primordial black holes passing through them, ruling out significant populations in this mass range. Gamma-ray observations from Hawking radiation set limits on lower masses. Femtolensing of gamma-ray bursts, ultra-short brightening events that would occur if primordial black holes passed in front of distant bursts, constrain the range from 10-17 to 10-22 grams. Current limits suggest primordial black holes in these ranges contribute less than 1% of dark matter. Gravitational microlensing surveys provide powerful constraints at higher masses. When a primordial black hole passes in front of a background star, gravitational lensing briefly brightens the star. The brightening duration depends on the black hole's mass and velocity heavier. Slower black holes cause longer events. The Mako and Eros collaborations monitored millions of stars in the Large Magellanic Cloud for microlensing events over decades. They detected some events, but too few to explain dark matter. The results ruled out primordial black holes with masses from 10-7 to several solar masses as the dominant dark matter component. The intermediate mass range from 10 to 100 solar masses remains intriguing. LIGO's detection of gravitational waves from merging black holes in this mass range sparked speculation that these could be primordial rather than stellar black holes. Primordial black holes would form in binary systems if two black holes formed near each other in the early universe. These binaries would gradually merge through gravitational wave emission, producing detectable signals today. The merger rate depends on the primordial black hole abundance. More primordial black holes mean more mergers. However, several lines of evidence argue against primordial black holes as the primary dark matter. Wide binary stars, pairs of stars separated by thousands of astronomical units, but gravitationally bound, would be disrupted if primordial black holes constituted most dark matter. The black holes would occasionally pass through binary systems, gravitationally perturbing the stars and breaking the pairs apart. Observations show wide binaries are common and stable, constraining primordial black hole abundance to less than about 30% of dark matter in the relevant mass range. Ultra-faint dwarf galaxies provide another constraint. These tiny galaxies orbiting the Milky Way contain very little visible matter, but appear to have substantial dark matter halos based on stellar velocities. If dark matter consisted of primordial black holes, dynamical friction, gravitational interactions between black holes and stars would cause the black holes to sink to the galaxy center, creating a dense core. Observations show these galaxies have constant density cores, not the cusps expected from primordial black holes. This argues against black holes being the dominant dark matter component. The cosmic microwave background structure also constrains primordial black holes. If significant primordial black hole formation occurred, it would have left imprints in the microwave background fluctuations. The energy released during black hole formation would have affected the ionization history and temperature fluctuations. Planck satellite measurements show no such signatures, limiting how many primordial black holes could have formed in the early universe. Despite these constraints, some windows remain where primordial black holes might contribute to dark matter without violating observations. The mass range around 10-20 grams faces weaker constraints than adjacent ranges. Black holes with masses around 30 solar masses might avoid some constraints while explaining LIGO's detections. Controversially, some researchers argue that asteroid mass primordial black holes could constitute all dark matter if their spatial distribution differs from assumptions used in deriving constraints. The mirror universe model provides an alternative explanation that avoids primordial black holes' difficulties. Mirror universe matter interacts only gravitationally with our universe, naturally explaining dark matter's properties without requiring exotic compact objects. The model predicts dark matter is distributed, like ordinary matter, in halos around galaxies rather than in point masses. Observations of galaxy dynamics, gravitational lensing, and structure formation all favor smoothly distributed dark matter over compact objects. Testing whether primordial black holes contribute significantly to dark matter requires future observations. The Nancy Grace Roman Space Telescope will conduct micro-lensing surveys sensitive to intermediate mass black holes. LIGO, Virgo, and CAGRA gravitational wave detectors will observe more black hole mergers, determining whether their masses and merger rates match primordial or stellar origins. Precise measurements of the cosmic microwave background's polarization by future experiments could detect subtle signatures of primordial black hole formation. The mirror universe hypothesis predicts that primordial black holes, if they formed in our universe, also formed identically in the mirror universe due to CPT symmetry. Both universes would contain equal populations of primordial black holes with the same mass distributions. But the model doesn't require primordial black holes to explain dark matter. Ordinary mirror atoms suffice. If observations definitively rule out primordial black holes as dark matter, the mirror universe model remains viable. If primordial black holes are discovered in significant numbers, the model must accommodate them in both universes symmetrically. Quantum entanglement across the mirror boundary. Quantum entanglement represents one of physics' most counterintuitive phenomena. Particles, separated by vast distances, instantaneously affect each other's states. Einstein famously called it spooky action at a distance, though modern understanding shows no information travels faster than light. In the context of a mirror universe, a fascinating question arises. Could particles be entangled across the CPT boundary, creating correlations between universes? While highly speculative, exploring this possibility reveals deep connections between quantum mechanics, cosmology, and the nature of the Big Bang singularity. Entanglement occurs when two or more particles share quantum states, such that measuring one particle immediately determines properties of the others, regardless of separation distance. The classic example involves photon pairs created with correlated polarizations. Measuring one photon's polarization as vertical instantaneously ensures the other is horizontal, even if they're light years apart. This isn't information transfer. You cannot control what measurement result you get, so you cannot send signals. But the correlations are real, measurable, and central to quantum mechanics. The phenomenon's strangeness led to the EPR paradox, named for Einstein, Podolsky, and Rosen's 1935 paper questioning quantum mechanics' completeness. They argued that either quantum mechanics' incomplete hidden variables determine measurement outcomes or action at a distance occurs, violating locality. John Bell's 1964 theorem showed these positions are testable. Experiments by Alain Aspect and others in the 1980s violated Bell's inequalities, confirming quantum mechanics and ruling out local hidden variables. Entanglement is real. Modern quantum information theory exploits entanglement for quantum computing, cryptography, and teleportation. Quantum computers use entangled qubits to process information in ways impossible for classical computers. Quantum key distribution uses entanglement to create absolutely secure communication channels. Any eavesdropping attempt disturbs the entangled state, revealing the intrusion. Quantum teleportation transfers quantum states between locations using entanglement and classical communication, though no faster than light travel occurs. The connection to cosmology enters through the universe's quantum initial state. The Big Bang singularity in the CPT symmetric cosmology is a boundary condition where quantum fields in both universes emerge from the same quantum state. This raises the possibility that particles in our universe might be entangled with particles in the mirror universe if they originated from the same quantum fluctuations at the singularity. Such entanglement would connect universes that cannot otherwise interact except gravitationally. Quantum field theory in curved space-time predicts particle creation through various mechanisms. During inflation, the rapid expansion preceding the hot Big Bang quantum vacuum fluctuations were stretched to macroscopic scales, seeding density fluctuations that became galaxies. This process creates particles in entangled pairs. Hawking radiation from black holes involves similar particle creation, where particles inside and outside the event horizon are entangled. The mirror universe scenario could involve analogous processes at the singularity. Consider a quantum fluctuation at the Big Bang creating a particle pair, with one particle entering our universe and the partner entering the mirror universe. If these particles remain entangled, measurements in our universe would correlate with measurements in the mirror universe. But this correlation would be undetectable from within either universe. We cannot access the mirror universe to perform measurements that would reveal entanglement. The correlation exists mathematically, but has no observable consequences within a single universe. This raises philosophical questions about the meaning of entanglement when measurement is impossible. In standard quantum mechanics, entanglement is operationally defined through correlations in measurement outcomes. If measurements cannot be performed on both parts of an entangled system, does the entanglement have physical meaning? Some interpretations say, yes, the quantum state exists independently of measurement. Others say no quantum states are only meaningful in terms of possible measurements. The many worlds interpretation of quantum mechanics offers an interesting perspective. In this interpretation, measurement doesn't collapse quantum states. Instead, the universe splits into branches corresponding to different outcomes. The mirror universe could be viewed as a permanent branching at the Big Bang singularity, a cosmic split into CPT conjugate copies. Entanglement across the boundary would represent quantum correlations between branches that diverged at the universe's origin. Mathematically modeling cross-universe entanglement requires careful treatment of quantum field theory on the CPT symmetric spacetime. The wave function of the universe would have support on both sides of the singularity, describing both universes simultaneously. Entanglement entropy, a measure of quantum correlations between the two sides, would quantify how much information one universe's state provides about the other. If the universes emerged from a pure quantum state, they would be maximally entangled initially, though classical evolution would decohere this entanglement over time. Decoherence is the process where quantum systems lose coherence through environmental interactions, transitioning from quantum to classical behavior. For cross-universe entanglement to have observable effects, it would need to survive decoherence for billions of years. Given that entanglement is notoriously fragile, even microscopic systems decohere in microseconds without careful isolation. Macroscopic cross-universe entanglement seems implausible. The gravitational and matter interactions each particle experiences would destroy quantum correlations almost immediately. However, certain protected quantum states might maintain entanglement longer. Topological quantum states, for instance, store quantum information in global properties resistant to local disturbances. If the universe's quantum state has topological character, some entanglement across the mirror boundary might survive. But detecting such entanglement would require measurements across both universes simultaneously, technologically impossible given the universe's separation. An observable consequence might appear in cosmological observables if cross-universe entanglement affects large-scale structure. If quantum fluctuations during inflation were entangled across the boundary, correlations might appear in cosmic microwave background fluctuations or galaxy distributions. But standard inflation produces quantum fluctuations independently in each universe. There's no mechanism for creating cross-universe correlations in conventional models. The CPT symmetric initial condition would need special properties to generate such correlations. The black hole information paradox provides an analogy. When matter falls into a black hole, information appears lost, violating quantum mechanics' unitarity, the principle that information is conserved. Hawking radiation partially resolves this by carrying information back out, but the mechanism remains debated. The mirror universe scenario involves similar information theoretic questions. If universes are entangled, where is the information about correlations stored? The answer likely involves the quantum state of the entire CPT symmetric spacetime, not reducible to either universe alone. String theory and quantum gravity approaches offer frameworks for addressing these questions. The holographic principle suggests that information about a volume of space is encoded on its boundary. For the mirror universe, the Big Bang singularity is a boundary between universes. Holography might imply that quantum information about both universes is encoded on this boundary, with entanglement representing correlations in the boundary data. But these ideas remain highly speculative, lacking experimental tests. Practically, cross-universe entanglement has no implications for technology or observations within our universe. Even if entanglement exists, we cannot exploit it for communication or computation because accessing the mirror universe is impossible. The entanglement would be a mathematical feature of the total quantum state, describing both universes, without consequences for measurements within either universe alone. It represents a conceptual curiosity rather than observable physics. The integrated Sachs-Wolf effect. Light traveling through the universe doesn't simply move through empty space. It traverses evolving gravitational fields created by the cosmic web's structure. As photons from the cosmic microwave background journey to our telescopes, they fall into gravitational potentials of galaxy clusters and climb out of voids. In a static universe, energy gained falling in would exactly cancel energy lost climbing out. But the universe expands, and in the presence of dark energy, gravitational potentials change with time. This creates net energy shifts, called the integrated Sachs-Wolf effect, providing direct evidence for dark energy and testing whether the mirror universe's gravitational influence matches predictions. The effect was predicted in 1967 by Rainer Sachs and Arthur Wolf as a consequence of general relativity's treatment of light in evolving spacetimes. They showed that photons traveling through time-varying gravitational potentials experience energy shifts. If a potential well becomes shallower as a photon traverses it matter dispersing due to expansion, the photon gains net energy, becoming bluer. If a potential becomes deeper matter clustering despite expansion, the photon loses energy, becoming redder. These shifts leave imprints in the cosmic microwave background's temperature pattern. Two epochs produce significant integrated Sachs-Wolf signals. The early integrated Sachs-Wolf effect occurred during the first billion years when radiation density still influenced expansion. During this period, gravitational potentials evolved as the universe transitioned from radiation to matter domination, creating temperature fluctuations in the microwave background. The late integrated Sachs-Wolf effect began roughly 5 billion years ago when dark energy became dynamically important, causing expansion to accelerate and gravitational potentials to decay. The late integrated Sachs-Wolf effect provides direct dark energy evidence. In a matter-dominated universe, gravitational potentials remain constant, clustering matter balances, expansion's dilution. But when dark energy dominates, expansion accelerates, overwhelming gravity's attraction. Potential wells become shallower over time as expansion pulls matter apart faster than gravity can cluster it. Photons traversing these decaying potentials gain energy, creating systematic temperature correlations with the large-scale structure. Detection requires correlating cosmic microwave background temperature maps with large-scale structure maps showing galaxy or dark matter distributions. Photons passing through regions that became galaxy clusters should show systematic temperature shifts compared to photons passing through regions that became voids. This correlation was first detected in 2004 by several independent teams using data from the Wilkinson Microwave Anisotropy Probe satellite and galaxy surveys, including the Sloan Digital Sky Survey and 2-micron All-Sky survey. The detection process involves sophisticated statistical techniques. Researchers create temperature maps from microwave background observations and mass distribution maps from galaxy surveys or gravitational lensing. They then measure the cross-correlation, how microwave background temperature varies when looking toward or away from mass concentrations. Positive correlation at large angular scales indicates the integrated Sachs-Wolf effect. The correlation amplitude depends on dark energy's properties. Stronger dark energy produces larger effects. Multiple independent analyses have confirmed the detection using improved data from the Planck satellite and deeper galaxy surveys. The combined significance exceeds 4 sigma, less than 0.01% probability of occurring by chance if no effect exists. The measured amplitude matches predictions for a universe with 68% dark energy, consistent with supernovae and baryon acoustic oscillation measurements. This concordance strengthens confidence in dark energy's existence and properties. The integrated Sachs-Wolf effect constrains dark energy's equation of state, the ratio of pressure to density. Different equations of state produce different evolution rates for gravitational potentials, changing the effect's amplitude. If dark energy has an equation of state W equals -1, corresponding to a cosmological constant, potentials decay at a specific rate. If W differs from -1, the decay rate changes. Current measurements are consistent with W equals -1, but allow modest deviations. In the mirror universe model, both universes undergo identical expansion histories in their respective time directions. Each universe experiences the transition to dark energy domination at the same cosmic epoch, measured in their local time coordinates. Gravitational potentials in both universes decay identically, producing integrated Sachs-Wolf effects of equal amplitude. From our perspective, our universe's microwave background shows temperature-mass correlations. The mirror universe's microwave background, if observable, would show identical correlations in their frame. The gravitational coupling between universes adds complexity. If mirror universe matter contributes to our gravitational potentials, the total potential evolution depends on matter distributions in both universes. However, if CPT symmetry ensures mass distributions are identical, the combined potential evolves identically to a single universe, with twice the matter equivalent to adjusting the matter density parameter. Observations constraining matter density would implicitly constrain this combined contribution. Future surveys will measure the integrated Sachs-Wolf effect with greater precision. The Vera Rubin Observatory's legacy survey of space and time will map billions of galaxies across the southern sky, providing exquisite large-scale structure maps. Cross-correlating these with Planck's microwave background measurements will strengthen the effect's detection and tighten constraints on dark energy evolution. The Nancy Grace Roman Space Telescope will complement these measurements with infrared observations reaching higher redshifts, tracing structure evolution across more cosmic time. Systematic errors complicate integrated Sachs-Wolf measurements. Foreground contamination from dust emission, synchrotron radiation, and free emission in our galaxy can mimic cosmological signals. Researchers must carefully remove these foregrounds using multi-frequency observations that exploit their different spectral signatures. Instrumental effects, beam shapes, calibration uncertainties, and noise correlations also require precise characterization. The statistical significance of current detections includes conservative estimates of these systematic uncertainties. Alternative theories of gravity predict different integrated Sachs-Wolf signals than general relativity with dark energy. Modified Newtonian dynamics and related theories produce different potential evolution rates, changing the expected correlation amplitude. Some modified gravity models predict anti-correlation photons losing energy when passing through matter concentrations opposite to the observed positive correlation. The detection of the integrated Sachs-Wolf effect with the predicted sign and amplitude supports general relativity over many alternatives. The mirror universe model makes specific predictions, distinguishing it from other dark energy explanations. If dark energy arises from quantum vacuum energy balanced by CPT symmetry requirements, it should remain precisely constant over cosmic time equation of state, exactly W equals -1. Any detection of dark energy evolution would challenge this aspect of the model, suggesting dark energy is a dynamical field rather than vacuum energy. Current measurements allow for modest time evolution, but future surveys will test whether W remains constant to percent-level precision. Polarization measurements of the cosmic microwave background provide complementary, integrated Sachs-Wolf tests. As photons traverse evolving potentials, not only does their energy shift, but their polarization rotates through gravitational effects. This rotation creates a specific pattern in polarization maps that correlates with temperature fluctuations and mass distributions. Current polarization measurements lack the sensitivity to detect this secondary effect clearly, but future experiments targeting degree-scale polarization might succeed, providing independent dark energy confirmation.